QA, QB. So one is intermediate state and other is the final state. So why how I can conformly say it is not equal if these two final states or both intermediate state. If one is intermediate, also initial state must be the final state for them to be equivalent. So let me take this example so that you can clearly understand. So here I have taken two finite automatas A and B. Okay, so here I taken two automatas A and B. So now I'm checking whether these two are equivalent or not. When you say these two automatas are equivalent, when you get a pair of state, if both pair of state, let me take if pair of state both are holding the final state, or if both are holding the final state or intermediate state, both are holding the final state or intermediate state, then you can say those are equivalent. If one is the final, if another is the intermediate, means then the two automatas are not equivalent. So let me explain you with an example. This example, let me take the states and what are the inputs for these two automatas, C and D are the inputs. Okay, so first let's take the initial in automata A and automata B, finite automata. Yeah, having the initial state and the final state Q1, and here also initial state and the final state is Q4. Okay, so here the both are the same initial and the same final. So then you can say for this particular two states, the given automata is an equivalent only to that particular. So we need to check for all the pair of states. If all the pair of states are having both or the same states, then we can say that finite automata is an equivalent. So let me check. First I have taken the pair of Q1 comma Q4, Q1 and the Q4. Okay, so on input C, Q1 goes to Q1, and on input C, the Q4 goes to Q4. Okay, I have taken the initial and the final states. The first one and here the first one in this automata. And on input D, Q1 on D goes to Q2, and Q4 on D goes to Q5. So here what do you understand? The Q1 is the initial state as well as the final state, and Q4 is the initial state as a final state, and Q2 is the intermediate state, and Q5 is the intermediate state. Q2 and Q5 are the intermediate state. Means both the states are either the final state or the intermediate state. So then you can say the Q1 and Q4 are these two states are forming the finite automata that are equivalent. So these two are confirming that they're in the correct position. Means they are saying that two automatas are equivalent. So let me check with another pair. So this time I'll take this pair and this pair, the Q2 and Q5. So Q2 on C goes to Q3, and Q5 on C goes to Q6. Now coming on D, Q2 on D, okay, Q2 on D goes to Q1, so which is a final state, and Q5 on D goes to Q4. So this is also a final state. So here Q3 is an intermediate state, and Q6 are the intermediate state, and Q1 is a final state, and Q4 is a final state. So by seeing this, you can clearly say these two states are also these two states are equivalent, which are producing the same the final states or the intermediate state. So these are also forming helping in that the two automatas are equivalent. Now let me take another pair. So this time I'm taking Q3 and Q6. Q3, Q6. So Q3 on C goes to Q2. Q6 on C goes to Q7. Okay, now coming to D. Q3 on D go to Q3 itself, and Q6 on D goes to Q6 itself. So here what do you understand? Q2 is the intermediate state, and Q7 is the intermediate state. Q3 is the intermediate state, and Q6 is also intermediate state. So both the states are forming either final states or the intermediate state. So then it is also saying that the given two automatas are equivalent. Next, what state I need to be considered? So here the remaining one is here is a Q7, but here no more state is there. So now you need to check. Q3, Q6 is already forming new state. So here Q2, Q7 is the remaining one which doesn't form any new state. So let's take Q2 and Q7 this time. So now Q2 on C. Q2 on C goes to, sorry, here. I'm taking Q2 and Q7. Q2 on C goes to Q3, and Q7 on C goes to Q6. Now Q2 on D goes to Q1, which is the final state, and Q7 on D goes to Q4, which is also final state. So from these two states, what do you understand? This is an intermediate state, Q6 is an intermediate state, Q1 is a final state, and Q4 is a final state. Okay, now I reached all the states, and all the states are saying the pair of states that are coming from the transition function, those are either the final states or the intermediate states. Not if one is final and if another is intermediate, then you can say the given automata are not equivalent. But here in this case, all the pairs either forming the final states or forming the intermediate states. Then you can say this A and B are equivalent. So that condition you have to remember. The main thing to find whether the two automatas are equivalent or not, you need to check the transition function that you're getting a new pair is both pairs are forming the equal same set of, means either the final state or either the intermediate state it has to form. Then we can say it is an equivalent finite automatas. The two automatas are equivalent finite automatas. So in the next video, I'll take one more examples which more state is there. So now you need to check. Q3, Q6 is already forming new state. So here Q2, Q7 is the remaining one which doesn't form any new state. So let's take Q2 and Q7 this time. So now Q2 on C. Q2 on C goes to, sorry, here. I'm taking Q2 and Q7. Q2 on C goes to Q3, and Q2 and Q7. What state I need? States are forming. What do you understand? Q3 on D gets state, and it is also saying that the given two automatas are equivalent. Next, what state I need to be considered? So here the remaining one is here is a Q7, but here no more state is there. So now you need to check. Q3, Q6 is already forming new state. So here Q2, Q7 is the remaining one which doesn't form any new state. So let's take Q2 and Q7 this time. So now Q2 on C. Q2 on C goes to, sorry, here. I'm taking Q2 and Q7. Q2 on C goes to Q3, and Q7 on C goes to Q6. Now Q2 on D goes to Q1, which is the final state, and Q7 on D goes to Q4, which is also final state. So from these two states, what students, welcome back. Let's continue with the equivalence of two finite automata. So in the previous video, I explained one of the equivalent. Okay. So if one step for further. So in this condition, Q3 is an intermediate state. Okay, and it's and confirm it that the person is not. Hi students, welcome back. Coming to the next topic, that is the minimization of the DFA. Hi students, welcome back. If for every pair. Hi students, welcome back. Let's continue with our subject, the theory of computations are equivalent or not, that we need to be. Hi students, welcome back. Let's continue with our subject, the theory of computations. So in the previous video, I explained about how to convert NFA to DFA. If there is a non-deterministic finite automata, we can convert into the deterministic finite automata. Now in this video, I want to explain you the equivalence of two finite automata. So if you take any two finite automata, whether it may be a deterministic or Hi students, welcome back. Let's continue with the equivalence of two finite automata. So in the previous video, I explained one of the examples, so that example derives that A and B, the two finite automata. Hi students, welcome back. Coming to the next topic, that is the minimization of the DFA. So far you have seen so many topics on this non-deterministic and deterministic. Minimizing means we are going to reduce the number of states that are participating in the deterministic finite automata. If suppose 7 states are there in deterministic finite automata, try to reduce the states. and make it 3 or 4. If even though it reduced to 6 also, it's somewhat better when compared to the previous state. Okay, so now let's see the steps that has to follow for minimizing the DFA. So in this video, I just give the algorithm, that is the basic steps that you need to follow for minimization, and the next video I'll explain with an example. Okay, so let me try to explain the algorithm. Minimization of deterministic finite rotor. The first step, what you have to do, remove all the states that are unreachable from initial state via any set of transition. What it means? Suppose if Q1 is the initial state, okay, some Q1, it has to reach all the states. It has to reach all the states that are participating in the network. Okay, so like this. Let me take. Okay, so here 1, 2, 3, 4 different states are there. So here first is remove all the states that are unreachable. So here from Q1, 1 is reaching. Okay, if Q1 wants to reach 4, it can reach via any set of transitions. So from 1 to 4, it is going to reach. Okay, if you want to reach 2, it can reach. If it want to reach 3, it can reach. If it want to reach 4, it can reach. Suppose here this direction is like this. Okay, so this is the 4 and it is coming. So here remove all the states that are unreachable. So from Q1 to I want to go to 4. So can I go? This way it is not possible. Now let's check here. From 2 to 3. Okay, 3 to 1 I can go, but 3 to 4 I can't go because 4 is coming to 3 side. So here the 4 is unreachable. So just remove that 4 from the transition. So that is the first step. Remove all the states that are unreachable from initial state. From initial state to which state is not unable to reach, just remove that transition from that node from the transition. That's first step. Second, draw the transition table for all pairs of states. So after removing this state, draw the transition table for the remaining states. The remaining states, whatever that are participating in the network, those states has to further, you need to draw the transition table. Okay, next. Now split the transition table into two tables. So whatever the transition table I got, that table I want to split into T1 and T2. Why I'm splitting? Okay, let me tell you. First, follow the algorithm. Then you can, after seeing the example, you can clearly understand. So after removing the unreachable state, I draw the transition table. So I'm splitting the transition table into two tables, T1 and the T2. Now T1 contains all final states and T2 contains non-final state. Means here initial state is also there. Non-final state and initial state. So T1, suppose in a deterministic finite automator, you can get one or more final state. That we know that. So if whatever the final states that are there, that final state should be is one table, and the remaining initial and intermediate state will be in another table. T1, T2. T1 contains all final states. T2 contains non-final states. Now step 4. Okay, I divided the two tables, one transition table into two tables. Next, what I have to do? Now find similar rows from table T1. So if you take the T1, you need to find the similar rows. I have drawn the transition table, right? So in this, I need to find the similar rows. So that is the transition function. Let's say A and B is input, and this is the transition function you get. Okay, you get here the transition function. If transition function, let me take Q and R. If transition function of QA is equal to the P, and the transition function of Q on A is equal to P, so here also you'll get the same P and P. Okay. If you are having the similar rows, so this Q and R is having the similar rows P, 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 P. Okay, in that case, that is find two states which have the similar values of A and B. A and B is having the same similar values, same states P, 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 and remove one of them. So here these two are equal. So just remove one state. One row you have to remove. Means I'm reducing, I'm minimizing my table. So remove one and replace here. Repeat step 3 until we find no similar rows available in T1. So in the same way, repeat step 3 and 4 for table T2 also, because I divide the table into two tables. One contains the final states and another contains the non-final states. So after removing the same rows, you'll get a new tables. Now combine the reduced T1 and T2 tables, and finally the transition table of minimized deterministic finite automata you'll get. Okay, so this is an algorithm for the minimizing. So in the next video, I'll explain with an example by taking these steps. Okay, thank you. Hi students, now let's continue with the minimization of DFA. In the previous video, I explained with an algorithm. Now let's see the example on this minimization of DFA. So here I have given, they are given one DFA, deterministic finite automata. I want to reduce the number of states in this finite automata so that you can say it is minimized. So what's the first step? First step means what is that? In a given DFA, I need to remove the unreachable states. Okay, so whatever the states that are unreachable from the initial state, that state has to be removed. So check. So here in the Q0, I'm reaching to Q1. Okay, I'm reaching to the Q2. How I'm going to reach the Q2? Okay, so here I'm not going. So come here. So from this also I'm not going to Q2. Okay, so from here also I'm not going to Q2. So then Q2 is unreachable. In the same way, check for the remaining thing. Q3 reachable, Q1 reachable, Q5 is also reachable. Q0 to Q3, Q3 to Q5. Means with the help of the intermediate states also, you have to reach from initial state to that state. But here Q2 is not, I'm not able to reach. Now check for Q4. So from this way, no, there is no possible. And come here from this way, Q3 and Q5. I'm going to Q5, but I'm not going to Q4. So from initial state, I'm not able to reach the Q4 states. So just remove Q2 and Q4 in finite automata. Okay, because these are unreachable states. Okay, so now these two are removing from the state. So I get only the four states: Q0, Q1, Q2, Q0, Q1, Q3, and Q5. So what's the second step? I need to draw the transition table. So after drawing the transition table, no need to check the diagram. Okay, so from this way, no, there is no possible. And come here from this way, Q3 and Q5. I'm going to Q5, but I'm not going to Q4. So from initial state, I'm not able to reach the Q4 states. So just remove Q2 and Q4 in finite automata. Okay, because these are unreachable states. Okay, so now these two are removing from the state. So I get only the four states: Q0, Q1, Q2, Q0, Q1, Q3, and Q5. So what's the second step? I need to draw the transition table. So after drawing the transition table, these are unreachable states. Unreachable states. Q1, Q3, and Q1. Okay. So rest of okay. So Q0 is the initial state. I know that. Now let me check. Q0 into in the same way I'm writing for the remaining states also. Q5 itself. Okay. So now I constructed the transition table. So now what is that? The next step 3. Step 3. What is the step 3 according to our algorithm? Divide the table into two tables. Now divide the table, rows of a transition table, into two sets. One is the T1 and the T2. So one transition is of starts with table which starts from non-final states. Table. Let me take the fresh page. Step 3. Table which starts from non-final states. So what are the non-final states? So here the final states are, sorry, I didn't write the final states. Only the initial state I have written. Q0 is the initial state, and here the final states are Q3 and Q5. These two are the final states. So what are the final states? The final states are non-final states. So what are the non-final states? So here the final states are, sorry, I didn't write the final states. Only the initial state I have written. Q0 is the initial state, and here the final states are Q3 and Q5. These two are the final states. So what are the final states? The final states are Q3 and non-final states. What are the non-final states? These two are the final states. So these two comes under one table, and these two comes under the another table. So I'm splitting these two. These are the non-final states, and these are the final states. So I'm taking T1 and the T2. Tables which start from non-final states are Q0 and Q1. So on 0 and 1, it goes to Q1 and Q3, Q0 and Q3. So another table which starts from final state. So that is Q3 and Q5. These are final states, 0, 1. On 0 it is going to Q5, here also Q5, Q5, Q5. So now coming to the step 4. So what's the step 4? So I had taken the DFA, I removed the unreachable states. After that, I had drawn the transition table. So after that, I split the table into two tables, T1 and T2. One contains non-final states, another contains final states. Okay. So now I need to check whether they are having the similar rows or not. So in this first table, you are getting the similar rows, Q1, Q3. Not similar. Q0, Q3. Not similar. These two tables are not similar. These two rows are not similar because here these two are same, but these two are not same. Okay. You can say set 1 has. Let me write here in step 4. Set 1 has no similar rows. Okay. No similar rows. So they will be same. So don't change anything in this table. Now coming to this table. So here, this this table has two rows having the same fields Q5, 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 Q5. So in the set 2, the row 1 and the row 2 are similar since Q3, Q5 transist to the same state 0 and 1. So just skip Q5 state, then replace Q5 by Q3 in the rest of the states. Okay, set 2 has similar rows. So skip Q5 and then replace Q5 in place of replace Q5 by Q3. So wherever Q5 is there, just replace in the place of Q5 with Q3. Okay, so in the rest of states. So what's the new state here? The table 2. So I just keep this Q5 and then replace Q5 in place of replace Q5 by Q3. So wherever Q5 is there, just replace in the place of Q5 with Q3. Okay, so in the rest of states, replace Q5 by Q3 in the rest of the same state 0 and 1. So just skip Q5 state, then replace Q5 by Q3 in the rest of the states. Okay, and this table has two rows having the same fields Q5, 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 Q5. So in the set 2, the row 1 and the row 2 are similar since Q3, Q5 transist to the same state 0 and 1. So just skip Q5 state, then replace Q5 by Q3 in the rest of the states. Okay, set 2 has similar rows. So skip Q5 and then replace Q5 in place of replace Q5 by Q3. So wherever Q5 is there, just replace in the place of Q5 with Q3. Okay, so the rest of it. So what's the new state here? The table 2. So I just skip this row and you'll get Q3. In the place of Q5, I have to write Q3, Q3. Okay, now combine the two rows. So this is my new table and this is another table. Now combine the table in the step 6. Step 6. Combine set 1 and set 2. After combining the set 1 and set 2, you'll get the new transition table. So what is the new transition table? Is the state 0, 1. So what is the state? The first table contains Q0. I didn't change the first table because it doesn't have any singular rows. So another table, it's this is the initial state and Q3 is the final state. In place of Q5, I need to write Q3. So this is my final transition table. And what's the transition diagram for this? Q0, Q1, and only 3 states. So here how many states? 1, 2, 3, 4. We are having, this is the 0, 1, 1 and 1. So this is the data. Hi students, welcome back. Coming to the next topics in the subject TOC, that is the theory of computation, real emissions and the Moore emissions. So these are the very important concepts in this subject. Now me explain you what is this Miller machines. So before going to know about these Miller machines, let me just recall the things. The finite automata are of two types. One is without output, and another is with output. So this I already discussed in the starting of this concepts. So the without output is deterministic finite automata, non-deterministic finite automata, non-deterministic finite automata with epsilon. So these are without output. Now we are came to this station, that is the finite automata with output. So this the finite automata with output or Miller machine and Moore machine. So these two machines will generate an output, whereas the finite automata without output are DFA, NFA, NFA epsilon. Okay. So now let's see. As there are two types of finite state machines which generates the output. So which generates the output? What are the two finite state machines? That is the Miller machine and the Moore machine. So in this video, I want to just give an introduction, the definition of the Miller machine and a simple example on Miller machine. So a Miller machine is a finite state machine whose output depends on the present state as well as the present input. So this thing you have to remember that. So whenever you have seen Miller machine depends on the output. The output depends on state machines which generates the output. So which generates the output? What are the two finite state machines? That is the Miller machine and the Moore machine. So in this video, I want to just give an introduction, the definition of the Miller machine and a simple example on Miller machine. So a Miller machine is a finite state machine whose output depends on the present state as well as the present input. So this thing you have to remember that. So whenever you have seen Miller machine depends on the output. The output depends on present state as well as present input. Okay, so this point you have to remember that. So this is the main difference between indicates the Miller machine and the Moore machine. Moore machine is the output depends on only on the present state, but here in the Miller machine it depends on present input as well as the state. Remember this. Okay, so the Miller machine depends upon the present input as well as the present state, whereas Moore machine depends upon the output. The output is depends upon only on the present state, not on the input. Okay, so don't be confused. So the more you practice, the more you can get this concept. It's a very easy. The Miller machine is a finite state machine whose output, whose output it depends on the present state. So whatever the present state, that it is working on the present state as well as the present input. Okay, so the definition for this Miller machine is it can be described as a six tuples, whereas in the deterministic finite automata, non-deterministic finite automata, it describes the five tuples. But here we are describing it six tuples because here we are going to generate an output. The Miller and Moore machines generates the output, whereas the deterministic and non-deterministic finite automata will not generate an output. So the Miller machine is described by six tuples: the Q, sigma, O, or you can call it as in this triangle. So delta X is an out X and Q naught. So now let's see what are these six tuples are. Here the total six tuples are there. So what are the six tuples indicate? Q is a finite set of states. So just like finite automata, deterministic and non-deterministic finite automata. Sigma is also the finite set of symbols called input alphabets. So sigma is going to generate the input alphabets, either it is from zeros and ones, or it is A or B, or in special characters also. Okay, the finite set of symbols called input alphabet. Now this is another thing, that is the O. You can represent like this also in some textbooks. So the O is a finite set of symbols called output alphabet. So this is one extra concept when compared to the deterministic and non-deterministic. The Miller machine is having a tuple O is a finite set of symbols called output alphabets. So here it's some input alphabets are there and output alphabet is there. And delta is the input transition function. So where Q into sigma gives the next state only. So just like a deterministic finite automata. And coming to X is the output transition function where X belongs to whenever the current state with any input alphabet gives the output alphabet. The current state with any input alphabet leads to the output alphabet. So rather than the final state, so here in the Miller machine and Moore the machine, you don't have the final states. Remember that only the initial state will be there, that is the Q naught. So in the same, there in the deterministic and non-deterministic, there is the initial state Q naught, and here is also the initial state is Q naught. But in Milli and More machine, there is no final state. We are having the output transition function. The extra one, these are the two concepts. So instead of final state, we will have the output transition function, that is x, that is the current state into some input on input alphabets leads to the output alphabet. So what are the 6 tuples? One is a set of states, and is a set of input symbols, and another is a set of output symbols, and this is the input transition function, output transition function. Remember this. This is input transition function. The sigma is the input delta is the input transmission function. X is the output transition function, and Q naught is the initial state. So let me explain you with a simple example. So here I'm given a Milli machine. I said the Milli machine, the output is depends upon the current state as well as the present state as well as the present input. So for output, the particular output depends upon the present state as well as the present input. Okay, and here the output is depends upon the present state as well as this present input, present state and present input, and you'll get some function, transition function, and the present state and present input, you'll get some transition function. Okay, so here they are given a table. This is a Milli machine table. So by seeing this Milli machine table, you can draw the transition diagram. Okay, so let me explain you here. So if I rotate the page, it will be confused for you. So how many states here total? You are having 4 states. Let me take the 4 states: A, B, okay, C, D. So I have taken the 4 states. So these 4 states. So on input 0. So what it's saying on input 0. So on input 0, it is going to the state B. It is going to the state B on input 0. On input 0, the present state is going to the state B and producing the output x1. So this is a representation. So this is an input and this is the output for the particular transition. If this state wants to go to another state, it generates on input 0. Hi students, let's see the examples of the Milli machine. So here they are given a question like, hi students, welcome back. The input stream. They ask the questions, then you need on the present itself. What is generating output is x3. So input 1 is going to D itself. And generating output x2. So this is a state transition diagram by seeing the transition table. So with the help of the table, you can draw the diagram also. Okay. So in the next videos, I'll explain more examples of the Milli machines, the different ways they ask the question. Hi students, let's see the examples of the Milli machine. So here they are given a question like the construct a Milli machine that produce one's complement of any binary input stream. Okay. So this is the general questions they are asking. The thing here is I need to construct a Milli machine. So how I can construct the Milli output? Okay. This one, the output is A on using this. Milli machine, I need to find out the output. The output should be the complement of the given input. Let's see. It is going to A itself, and the output it is generating is 0. So 0, 1, 0. So A on getting input 0, it gives the output 1. Video I explained 8. Let's take a state. Okay. So if I take the input 0, if I take an input 0, the output it generates is 1. Okay, so here this is an input and it generates the output. So this is a representation of the Mealy machine. Okay, in the previous video I explained how you're going to construct a Mealy machine. So for the given input, the output is 1. Means the complement of 0 is 1. In the same way, suppose if the input is 1, the output it generates is 0. Okay, so A on getting input 0, it gives the output 1, and A on getting 1, it gives the output is 0. So you can take any one of the string, then you'll see the output. Suppose if I take the input 1, 0, 1. Okay, so A on 1, A on 1, A on 1, A on 1, what it is generating? Again A only. What is the output? Output is 0. Okay, now A on 0. Next one, A on 0. So A on input 0, what is the output it generating? It's going to A only. The output it generating is 1. So the remaining one is 1. Now A on 1, the A on 1 input is going to A only. What is the output it generating? 0. So did you observe here? The input they are given is 1, 0, 1, and the output it generates is 0, 1, 0. So in place of 1, it is coming 0. In place of 0, it is getting 1. Okay, if you want, you can take one more example. Let me take whatever the string that you want. Let me take suppose 1, 1, 0, 1. Let me see, this is an input string they are given. I want to, by using this Mealy machine, I need to find out the output. The output should be the complement of the given input. Let's see. So first, A is initial, A on 1, it is going to A itself and it is generated. So did you get the complement of the given string? So the given string is 1, 1, 0, 1 and the output is 0, 0, 1, 0, just the complement of the given string. Hi students, let's continue with the examples of the Mealy machine. Now here in another example, construct a Mealy machine that prints A. Okay, so that prints A whenever the sequence 0, 1 is encountered in any input binary string. So they are saying any input binary string means it should be in the 0 and 1. Okay, so whatever the input binary string, okay, this is an input alphabet. So the input they are giving the string, like suppose whatever the string we are taking, and the output alphabet O is AB, set of the string AB. Okay, so now let me construct how to construct this Mealy machine. So first construct the deterministic finite automator for the given question. So then it will be easy for you because here they are saying length is 2, number of states is length plus 1. You'll get the number of states, that is 3 states. So this is the start. Let's say A is initial. 0, 1 is encountered. It has to print the output has to print A. So whenever it is B as 1, input 1, the output should be A. So whenever the 0, 1 is encountered, the output it has to print A, and the remaining all are B's. Remember that the remaining all means, so in the deterministic finite automator, each state has to construct in zeros and the ones. So it is going out 0 and the input 1 B. So the remaining, for all the remaining things you just place. So 1 is going and the 0 is B, and the remaining all things you need to construct as. So here 1 is coming and C is going to 0 on input 0, 1 it should be B. Okay, so already C is going on 1, it is B. Okay, so this is a Mealy machine. So how can I only the thing here, whatever the string you are taking, okay, it generates whenever the sequence 0, 1 is encountered, it prints A. Okay, suppose if I take a simple 0, 1, 0, 0, 1, the final output it generates is A. Whenever the 0, 1 is encountered, it prints A. Okay. So let me take 0, 0, 0, 0, 1. In case of 0, 0, 1 also, if I take 0, 0, 1, in place of 1, A is encountered. So let me take an example to check whether this Mealy machine, whatever I constructed, is true or false. Okay, so let us assume a string as 0, 1, 1, 0. Let me take, okay, 0, 1, 1, 0. Next, and A on B, 0, 1. If the and the output it is generating is B. Now, it's going to be all B's. Sequence is not there, so I got the output as take the minimum 0. These each 1. So here A is generating 0 and 1. And the B is generating 0 as well as 1. And the C is generating. Hi students, welcome back. Hi students, let's continue with the examples of the Mealy machine. Now here in Hi students, let's continue with the examples of the Mealy machine. Now here in another example, construct a Mealy machine that prints A. Okay, so that prints A whenever the sequence 0, 1 is encountered in any input binary string. So they are saying. Hi students, welcome back. Now let's see another example to construct the Mealy machine. So here they're asking, I need to construct a Mealy machine which accepting a language, a string from sigma closure, where the input alphabets, so the sigma input alphabets is set of A comma B, and the string should end with either AA or B. So whatever the string that I have taken, that string should end with, okay, string should end with single A, it should be 0. Just keep the output 0 for the single A. So whenever A is encountered, it has to generate 1. Okay, now let me construct with the B. Whenever the string that ends with the B, So the input, this is B. Whenever the string that ends with BB, it generates an output 1 or else 0. So if the single B is there, the output is 0. If BB is there, the output is 1. Okay, so this is a simple concept. Whatever the question they are asking, I constructed a basic thing. On A, it should generate an output 0. So only for this, it is going to Q2 and generating an output Q2 on B, it is going to Q2 itself, and what is output is generating 1. So what is output? It generated 0 on B, Q0 on B, it is going to Q2, it is generating an output as 1. Okay, so only those strings which are generating AA and the BB sequence, for that the output is 1. Keep all the students, welcome back. Coming to the next topic, that is a Moore machine. So far you have seen about the Milli machine. Now coming to another one, that is a Moore machine. The main difference between the Moore machine and the Milli machine is, just recall the Milli machine, that the output is depends upon the present state as well as a present input. But in Moore machine, the output depends on only a present state. Okay, it depends only on the present state, not on the present input. But Milli machine, the output depends on present state as well as the present input. Okay, so a Moore machine can be described by 6 tuples. So just like a Milli machine, it is also described with the 6 tuples, the same definition. A Q is a finite set of states and sigma is a finite set of symbols called input alphabet, and O is a finite set of symbols called output alphabet, and delta is the input transition, and the transition function is Q into sigma is equal, yields to Q only. Okay, the correct table. Did you observe the difference of the Milli machine and the Moore machine in this table? There in the Moore machine, for the present state, okay, it depends on, for every input there is a separate output, because the Milli machine depends on the present state as well as the present input. But here in the Moore machine, the present state, the output is depends upon the present state only, not the input. Okay, so here the present state on input 0 goes to the B, on input 1 it goes to the C, and both the input 0 and input 1 are producing the output x2. And the present state B, on input 0 it goes to B, on input 1 it goes to D, and those input 0 and 1 both are producing the output x1. So here the inputs, whatever the input there is, but it produces an output, the same output for that particular input, for that particular state. For the present state, it produces an output, whatever that input. input may be. The present B output depends upon the present state only, whereas Miller machine, the output depends upon the present state as well as the present input. Thank you. Students, welcome back. Now let's see the examples of the Moore machine. 0 as an input and produce 1 as an output. And third is taking 1 as an input and produce 0 as an output. So total 3 states we require. So let's start the diagram. So here first of all you have to think what is the input they are given and what we need to try out, what we need to find out. We need to generate the ones complement of a given binary number. Whatever the binary number they are given, further we need to construct a ones complement. So total number of states that are required for this is, let's take Q naught. So for 0, Q naught is 0. Okay, so on 0 it is going to give 1 and generates an output 1. Suppose on 1, on input 1, okay, so the Q naught output is, here it is 0. So Q1 as well as 1 we had created a path. Okay, now coming to the Q2. Now Q2 has to create a path. So Q2 on 0, okay, so here Q2 on 0, it has to generate an output 1. Now Q2 on 1, it has to generate an output 0. So now this Moore machine is completed. How can I say it is this machine is completed? Because Q0 is going to generate taking the input 0 and 1 as well as the Q1 is also taking the input. And what is the output it is generated? It is 0. Okay, next. Students, welcome back. Now let's see the examples of the Moore machine. So here they're asking, I have to design a Moore machine to generate the ones complement of a given binary number. So the same question we are taken for the Melee machine also, but now let's see here. Hi students, welcome back. Let's continue with the examples of the Moore machine. Designing, we need to check 3 conditions. So what are the 3 conditions? Just now I type sequence either 1 0 0 and 0 0 1, whatever is the sequence. Remember that. So only I'm drawing the partial diagram. So after that, whatever generating on 0 as well as a 1. So this work is over. Now one on 1 you have generated 1 means its output should be the 0. So here if it's 0 means output should be the C only, because if other than the remaining strings all generated this output as C. Substring 101 and 1. Hi students, welcome back. Now A, B, A is over. Finally B is there. So Q0 on B. Q0 it is going to the state Q3 and on B goes to Q. Hi students, welcome back. Coming to the next topic in the subject theory of computation, in a new initial state Q, and so that is a closure under union. Mean concatenation and clean closure. So this is a so intersection. It is end, not complement, union, and complement, and the whole complement is nothing but M. Thank you. Hi students, welcome back. Coming to the next topic in the subject theory of computations is the closure properties of regular languages. So to implement whatever the regular language that we have taken, that having some closure properties. So based on the properties, the regular language can be said whether the language is accepted or it's not accepted. Okay, and not only that, so that can be explained by taking the theorems. But here the closure properties is going to tell what is the relationship between the languages that we are taking. If you are taking two languages, what is the relationship between them, and what is the output that we get while these two languages will be working together like that. So now let's see the closure properties of the regular language. The first closure property is closure under union. Okay, under union. So union means, you know that the symbol is U. Means whatever the language that we are taking, if you take the two languages, so the final string, if you union the two languages, that string either will present in the language 1 or it can present in the language 2. That is the union. Let's see the operation. If L and M are regular languages, let us take L and M or regular languages. So their union is defined by L union M. You'll get one string W. Okay, if you union L and M, these two languages, if you perform the union operation, you will get a new language W. So this W, that is a string. This string belongs to language L, or that string belongs to language M. That is the meaning of the union. Let's take another example. Let's take AL and AM, or the two finite automata. So we are saying that these two are the automata languages. So finite automata accepting the L and M respectively. Let's take the AL finite automata. So S is a starting string. So this in the finite automata, you are having only one initial state and one or more final states. Okay, this is a language. There is a finite automata which accepting the language L, and this is a finite automata which accepting the language M. So in these two diagrams, suppose if you perform union operation, is there a finite automata accepting L union M? Yes, obviously. How? Let's see. So if is there a finite automata accepting L union M? Yes, obviously. How? Let's see. So if you perform the union operation, so here I have taken a new initial state Q, and with epsilon moves means Q, it's nothing doing, it can go either to the S dash or S dash. So that is a condition. Whenever L union M is there, you'll get a new string such that that new string is either belong to language L or that new string is either belong to language M. In the same way, if Q is there, its initial state, without any input, either it can go to the S or either it go to the S dash. So this is a M and this is a L. So that string can either go to this side, either it comes to this side. Okay, so let L and M be a language of regular expressions, R and S respectively. Then R plus S is a regular expression whose language is L union M. So here nothing is there. Whatever the languages I have taken, that I am representing in the form of regular expression. So if you want to represent normally the language, you can say the union operation is L union M. If you want to represent this union operation in the form of regular expressions, you have to represent like R plus S. Remember that. L union M is represented like R plus S in the regular expressions. So you have to represent like R plus S. Remember that. L union M is represented like R plus S in the regular expression. Star. The same idea can be applied using clean closure. Languages in LM. Okay, means R and S are the regular expressions, and those languages are L and M. Suppose if R star is a regular expression, obviously those languages should be L star. That is a closure. closure under concatenation whose language, mean concatenation and the clean closure. So this is a concatenation and this is a clean closure. So here R is for the regular expressions whose language is in LM, which is a concatenation, and suppose if R star is a regular expression and whose language is in L star, it's a clean closure. Now coming to the another property, there is a closure under intersection. So intersection, if L and M are regular languages, so their intersection can be defined as L intersection M is equal to W, a string, such that a string is either belongs to L and either belongs to M. It is AND, not OR. OR means it is union. AND means it is intersection. So using De Morgan's law, we can represent L intersection M is equal to, if you want to represent this L intersection M in terms of union, you can take L complement union M complement, and the whole complement is nothing but L intersection M. So that is the De Morgan's law. Thus, there must be a finite automata accepting L intersection M. Thank you. Hi students, let's continue with the closure properties of the regular languages. So in the previous video, I explained about the closure under union, closure under concatenation and clean closure, and the closure under intersection. Okay, so now let's see the closure under difference. Let L and M are the two languages, then their difference is defined as L minus M. So you know the difference symbol, minus. So L minus M is equal to, you'll get a string. So that string belongs to L, and whatever the string that you got, that does not belong to the M language. Okay, so if you perform L minus M operation, you have to take only the terms that are present in the L, items that are present in the L. You won't take the elements that are present in the M. Okay, so when you perform L minus M, you'll get one new string. So this string will be present, belongs to L, and it does not belongs to M. That is the difference, closure under difference. So using De Morgan's law, you can also write L minus M if you want to represent in the form of the intersection. L minus M is equal to L intersection M complement. So if you perform L intersection M complement, you'll get L minus M only. Means the terms that are present only in the L, not in the M. So thus there must be a finite automata for L minus M. Now coming to the another closure, the closure under complementation in the L, not in the M. So thus there must be a finite automata for L minus M. Now coming to the another closure, the closure under complementation. So these are all the different closure properties of the regular language. Now let's see the closure under complementation. The complement of a language L, that is with respect to an alphabet, we know that the sigma is an alphabet, such that sigma star also contains in L. Okay, so whatever you are taking the language L, so that language, whatever you are taking, that should be with respect to the alphabet sigma. Okay, that is, it is in the range of 0, 1 if you take the binary numbers, or if you take the alphabets A to Z. So such that the sigma star contains L. That is, sigma star minus L is nothing but the complementation. Since sigma star is surely regular, we know that sigma star is surely regular. It's a regular language. Okay, the complement of a regular language is always regular. The complement of regular language is always regular. Now coming to the another closure property of regular language, there is a closure under reversal. It's just reversing. Whatever the input they are given, so that should be the output should be the closure property. The complement of a regular language is always, I'm taking two languages. Okay, one language I'm taking, if you can see. Okay, so reverse means, okay, this is a reversal. Suppose if you, in basis, if you take E as a symbol, epsilon, A or phi, then ER is equal to E, obviously. Okay. Hi students, welcome back. Now let's see the pumping lemma for regular grammars or regular language, whatever you're taking. So what is this pumping lemma and how we are applying on this regular grammars? Let's see. So here there's a theorem. So let L be a regular language. So let's take L, the language L be a regular language. Then there exists a constant P. Let me take a constant in this language L. That is a pumping lemma. I have taken one constant P such that for every string W, okay, in language, mod W, that is the length of mod W, should be greater than or equal to this constant. Whatever the constant that is present in the language, that is the length of the string should be greater than or equal to P. Greater than or equal to P. Remember this point. Okay, in the pumping lemma. So if we have taken a language L be a regular language, then there exists a constant P in this language such that for every string W in L. So in the language you'll have a string, right? You know that. The substrings are there. So in this language you are having a string W. That string should be the mod W. That is the length of that string should be greater than or equal to the given constant. Now we can break this string into three substrings. Okay, let me take the W into three strings X, Y, Z. Okay, such that it has to follow some conditions. That is the pumping lemma. Here the mod Y, that's a positive number, mod Y should be greater than 0. Okay, this should be greater than 0. And mod XY, is less than or equal to p means this side is less than or equal to p, not the greater than or equal to p. Okay, here complete the length of the string that mod w is greater than or equal to p, but here the mod xy is less than or equal to p. And the third condition is for all k greater than or equal to 0 means I'm taking one constant that is greater than or equal to 0 means above 0, then the string x, that is a 3 x y power k z is also in language L. So this is the theorem. It's a greater than or equal to the since pumping. Leave it. So for some languages, strings longer than p can be pumped to obviously regular, but we have to show it is not a regular. So this condition has to be followed. Then the condition is that satisfies all the three pumping grammars. Let's see. So here there's a theorem. So let L be a regular language. So let's take L, the language L be a regular language. Then there exists a constant P. Let me take a constant in this language L. There is a pumping lemma. I have taken one constant. Hi students, welcome back. Coming to the next topic in the Hi students, welcome back now. Hi students, welcome back. Let me take the k equal to xyz. So whatever the condition language that you are taken, just take the string and divided the string value here. So whenever I substitute the values, I got how to prove that the language is not L is not a regular. So just take contradiction and try to prove that, and we have to show that L is not a regular language. Hi students, welcome back. Now let's. Hi students. Hi students, welcome back. Now let's see the pumping lemma for regular grammars or regular language, whatever you're taking. So what is this pumping lemma and how we are applying on this regular grammars? Let's see. So here there's a theorem. So let L be a regular language. So let's take L, the language L be a regular language. Then there exists a constant P. Let me take a constant in this language L. There is a pumping lemma. I have taken one constant P such that for every string W, okay, in language, mod W, that is the length of mod W, should be greater than or equal to this constant. Whatever the constant that is present in the language, that is the length of the string should be greater than or equal to P. Greater than or equal to P. Remember this point. Okay, in the pumping lemma, so that is K in language, mod W, that is the length of mod W, should be greater than or equal to this constant. Whatever the constant that is present in the language, that is the length of the string should be greater than or equal to P. greater than or equal to P. Remember this point. Okay, in the pumping lemma, so if we have taken a language L be a regular language, then there exists a constant P in this language such that for every string W in L, so in the language you'll have a string, right? You know that the substrings are there. So in this language you are having a string W. That string should be the mod W, that is the length of that string should be greater than or equal to the given constant. Now we can break this string into three substrings. Okay, let me take the W into three strings X, Y, Z. Okay, such that it has to follow some conditions. That is the pumping lemma. Here the mod Y, that's a positive number, mod Y should be greater than 0. Okay, this should be greater than 0, and mod XY is less than or equal to P, means this side is less than or equal to P, not the greater than or equal to P. Okay, here complete the length of the string, that mod W is greater than or equal to P, but here the mod XY should less than or equal to P. And the third condition is for all K greater than or equal to 0, means I'm taking one constant that is greater than or equal to 0, means above 0, then the string X, that is a 3 X Y power K Z is also in language L. So this is the theorem, it's a theorem of the pumping lemma. It's a simple thing. By seeing this, you won't confuse. Let's take a concept. If I've taken a language L, that is a regular language. In that language, I'm having a constant P. Okay, and such that for every string W, here in the language you are having a string W. In W also you are having the P, right? So that should be mod W is greater than or equal to this constant. It should be greater than or equal to the constant. And we are breaking this into three strings X, Y, Z, such that what is the condition on these three strings? Mod Y should be greater than 0, mod XY should be less than or equal to P, and for all K greater than or equal to 0, the string XY power KZ is also in language. So let's see the proof, then you'll understand. Before going to that, let me explain what are the different applications of the pumping lemma. Actually, why we are using this pumping lemma? What is the use of the pumping lemma? The pumping lemma is to be applied to show that certain languages are not regular. This what is going to do? It is going to prove that some languages are not regular. For some languages you have to regular, that I have to be true, that not regular. To prove that a language is not regular using pumping lemma, we have to follow these steps. If you follow these steps, you can say that the language is not regular by using pumping lemma. At first, we have to assume L is regular. So starting, you take the contradiction. Let's assume whatever the language that I have taken is regular. Next, so the pumping lemma should hold this language L. Okay, now of this pumping lemma is holding this language L. So whatever the length it should be, holding the length L. It has to have a pumping length say P. I said some constant has to be present in that language. language. Okay, that is a pumping length, say P. Now, we are going to that should not belong to the language for some of n. Okay, that n should be, I should be greater than or equal to 0. That should be, that you have to remember that. Okay, the thing is, you have to show n and whatever it may be z, that should not belong to the language for some of n. Okay, that n should be, I should be greater than or equal to 0. That should be, that you have to remember that. Okay, the thing is, you have to show whatever the string that is divided into 3 parts, that string is divided and it holding the equation x y power k z, that should not belong to the language. Then you can prove that it's already proved that the given language is not regular. If it belongs to the language, then it is obviously regular, but we have to show it is not a regular. So this condition has to be followed. Then consider all ways that w can be divided into x, y, z. So you can check all the ways. Okay, I can prove this language as not regular. You have to check that. Then consider all the ways that w can be divided into x, y, z. Show that none of these can satisfy all the 3 pumping conditions at the same time. So you have to show that none of this whatever the condition is that satisfies all the 3 pumping conditions at the same time. Then w cannot be pumped. Okay, the thing is, you have to show belong to the language. Then you can so you can check all the ways. Okay, I can prove this language as not regular. You have to check that. Hi students, welcome back. Now let me explain you the example of pumping lemma. So here our concept is I have to take one language, a regular language, and I have to show that regular language is not the language that I have taken is not regular by using pumping lemma. Okay, so here I have taken prove that L is equal to a power I b power I is I whatever the I have taken it should be greater than or equal to 0. Means it should be greater than 0. Okay, a power 0 b power 0 is not accepted. I have how many states that I will get? Suppose if a square means a into a I get. Okay, and b cube means b into b into b. So total how many? Means I get a power n b power n. Okay, a power n b power n. Thus mod w is equal to 2n. So already 2 states are there. Okay, 2 states are there. Okay, 2, 1, 2. So I have write 2. So I don't know still how many states that I will get. Suppose if a square means a into a I get. Okay, and b cube means b into b into b. So total how many? Means I get 2 into 3. So total n, how many n? So here 2 into 2 and 3. So like that. So further I have taken the mod w is equal to 2n. Okay, a and b are the two terms, and n is the number of terms, number of states that are representing. So here I have taken n is the number of states. Okay, 2n, and that should be greater than or equal to n. Now third step. By pumping lemma, let's take a string. We have to take one string, w is equal to x, y, z. So whatever the condition language that you are taken, just take the string and divide the string into 3 components, where mod x, y is less or equal to n. So let's take, I divided these x, y, z into 3 substrings. I have taken x is equal to a power t, and y is equal to a power q, and z is equal to a power n, b power n. Okay, so this is a 3 term I have, let us issue, because I have to take only these 2 strings a, b. Okay, so x is equal to a power p, and y is equal to a power q, and z is equal to a power n, b power n. And where these exponents p plus q plus r is equal to n. This is a condition. P plus q plus r is equal to n, and p should not equal to 0, and q should not equal to 0, and r is not equal to 0. Okay, thus mod y is not equal to 0. We know that x y power n into z. Okay, we have to show that it does not belong to the language. We have to show that. So I have taken the terms x, y, z values. Now let me take a simple. Let me take the k value. Means our equation is x power y, x into y power k into z. Okay, so this is a string. W is equal. This has to be satisfied. X into y power k into z. So let me take that k value is 2. That is x y square z. So in terms of, in place of x, substitute whatever the value that is there. So for x, what is the value? A power p, y a q, z a power r b n. Let's substitute the value here. So whenever I substitute the values, I got this equation. X y square z is equal to a power p, a power 2q, a power r, and b power n. Now number of a's. First let me calculate the number of a's. In the number of a's, these 3 terms are there. A's. So only take this exponents p plus 2q plus r. So I'm taking p plus q plus r plus q. You know that p plus q plus r is equal to n. Here the condition is there. P plus q plus r is equal to n. So substitute n plus q. Okay. Now x y square z is equal to a power, this complete p plus 2q plus r, a power 1 plus 2 plus 3. So in the same way apply the formula here. That formula. So p plus 2q plus value that is there equal to 0, and q should not equal to 0. So like that. So for and z is equal to a three substrings. I have taken x is equal to a power p and y is equal to a power q and z is equal to a power n b power n. Okay, so this is a three term I have let us issue because I have to take only these two strings a b. Okay, so x is equal to a power p and y is equal to a power q and z is equal to a power n b power n, and where these exponents p plus q plus r is equal to n. This is a condition. P plus q plus r is equal to n, and p should not equal to 0 and q should not equal to 0 and r is not equal to 0. Okay, thus mod y is not equal to 0. We know that xy power n into z. Okay, we have to show that it does not belong to the language. We have to show that x substitute whatever the value that is there. So for x, what is the value? A power p, y a q, z a power r d n. Let's substitute the value here. So whenever I substitute the values, I got this equation. X y squared z is equal to a power p, a power 2q, a power r and b power n. Now number of a's. First let me calculate the number of a's. In the number of a's, this three terms are there, a's. So only take this exponents p plus 2q plus r. So I'm taking p plus q plus r plus q. You know that p plus q plus x y. Hi students, welcome back. Let's continue with our subject theory of computations. The next topic in this subject is context-free grammar, CFG, context-free grammar. So what it means? A context-free CFG stands for context-free grammar. It is a formal grammar which is used to generate all possible patterns of a strings in a given finite language. Okay, so actually what does this context-free grammar? We call this as a formal grammar. Why we call this as a formal grammar? Because it is used to generate all possible patterns, whatever the patterns that are available of the string, that different patterns can be generated. It can be represented in leftmost or rightmost, in whatever it may be. Okay, so it can generate all possible patterns of strings in a given formal language. Okay. A context-free grammar G can be defined as four tuples. So far you have seen whenever we are discussing about the definition, the non-deterministic finite automata, deterministic finite automata, okay, whatever we are taking that, Miller machine and the Moore machine, every definition is based upon the tuples, and that definition is defined by the tuples. Okay, so in the same way for the context-free grammar also, it can be defined as a four tuples. So what are those four tuples? G is equal to VTPS, or you can call it as NTPS also. Okay, G is equal to VTPS. So what is this G and what is VTPS? Let's see that. So whenever you ask about the context-free grammar, you have to see that it is a formal grammar which is used to generate all possible patterns of the strings in a given formal language. Okay, and it can be defined as a four tuples. That is, graph is equal to VTPS. What is G? Sorry, it's a grammar, not graph. G is a grammar which consists of set of production rules. So this G, whatever the G that we are using, it consisting of set of production rules. So what's the use of those rules? It is used to generate the string of a language. So what type of string of language I'm going to get, that will be generated by this G grammar. So if you take with the help of these VDPs, a grammar is generated. This grammar is used to generate the string of language. Okay, what's the string of a language that I'm using? And coming to the T. T, you call it as a final set of terminal symbols. T means terminal. Remember that. Don't confuse. Terminal symbols. Terminal symbols means you can take it as a capitals. Okay. So sorry, it is terminal means lowercase letters. It's a lowercase letters means the small letters, alphabets, A, B, C, and all the letters that is lowercase. Okay, not having the least prior, lowercase. So T is the final set of terminal symbols. Terminal symbols means you have to remember that lowercase letters. Okay, the lowercase letters you call it as a terminal symbols. And coming to the P. P is the V is the final set of non-terminal symbols. I said T is a terminal symbol. T is a terminal symbol. And what about the V? V is a non-terminal symbols. We can represent it. It is denoted by the capital letters. The only difference between that two is V is represented in capital letters. The symbols that are represented in capital letters, symbols you call it as the alphabets or the binary numbers. Okay, or or special characters. That is the symbols. Okay, and here V is represented in the capital letters and T is represented in the small letters. That is the lowercase letters. Whenever you see in the production rules, whenever you're seeing like A, B, S, E, so these are called as a non-terminals. Non-terminals. Okay, so these are the sets of V. We represented it as V, non-terminals. And what about the T? T is the terminals. Terminals means A, B, C. So plus, minus, into, divide. So these are all terminal symbols. Remember that. Terminal symbols. There's a main difference between the non-terminal and the terminal. Okay, T is the terminal symbols, V is the non-terminal symbols, and coming to the P. P is a set of production rules which is used for replacing non-terminal symbols on left side of the production in a string with other terminals or non-terminals on right side of the production. But one thing that you have to remember that what is a production rule? A production rule means it consisting of, okay, this is the production rule you call it as, or S determines AS. So this is a production rule, or S determines B or A. Okay, so these are the different ways of representing the production rules. So here a production P is a set of production rules which is used for replacing the non-terminals on left side of the production. So these are the left side, which you call it as a non-terminals, because all are capital letters. Whenever these are left side, always it is a capital letters. Remember that left side should be capital letters and the right side should be capital as well as the lowercase letters. Okay, means this side, in the right hand side, you are having the terminals as well as the non-terminals. Just we talk in the terminology. Okay, or just remove that capital letters and the small letters because you have to use the terminology. Remember that terminals means lowercase letters, non-terminals means the higher case letters, that is the capital letters. So left hand side is always non-terminals. Left hand side of the production rule is always represented as a non-terminals, and right hand side should be represented in non-terminals as well as terminals. Okay, so this is a non-terminal, and this becomes a terminal. Terminal, and this is a terminal. So only the capital letters or the non-terminals, and the small letters or the terminals. I'm a little bit confused, so let me clear you once again. Left hand side should be non-terminals. The non-terminals are nothing but the capital letters. Terminals. Here, whatever it may be, tell you rules, and S is the start. Hi students, welcome back. In the previous video I explained about what is a context-free grammar. That is a context-free grammar. It's a combination of it's defined as a 4 tuples, VTPS or NTPS. V is a set of non-terminals, T is a set of terminals, and P is the production rules, and S is a start symbol. So here they're asking the question like, we need to construct the context-free grammar. Okay, one context-free grammar we have to be generated for a language having a number of A's over the set. Means any number of A's, having any number of A's. Okay, in the set only the A. The input symbol is only the A. Okay, so it can be represented in any number of A's. The language can be represented in any number of A's. That is including epsilon. You can include the empty string also, A. So like this, any number of A's. Okay, by seeing the question I have written like this. They're asking construct context-free grammar for the language having any number of A's. So any number of A's means it may be 0 or 1, 2, 3, 4, 5, any number of A's over the set. For this I need to construct the context-free grammar. How I can construct? So first let me write the regular expression for this grammar. The regular expression for this grammar is A star. Obviously, because A closure means A star means it's a multiples of A. A multiples of A can be represented in regular expression like this. Now coming to the production rules. First write the production rule for the context-free grammar. Okay, so the production rule for the regular expression, whatever the regular expression I got, by seeing this regular expression, I'm going to construct the production rule. So I'm taking the starting symbol S, A, S. Okay, and I take S as an epsilon. So I'm calling this as rule 1 and this is as a rule 2. Production 1, rule 1 and rule 2. Means S determines A means I'm replacing in place of S, AS. Okay, so in place of S I'm replacing S with epsilon. Okay, so the right hand side, whatever it may be, that should be replaced to the left hand side. So in the place of S I can keep epsilon. A epsilon means you get A only. So that is the regular expression that you are getting. So these are the production rules for the given regular expression. Now if you want to derive a string, let me derive a string. That is the input I'm taking. A, 6 A's. Okay, so this I need to be derived. The context-free grammar is set of non-terminals. Here I have taken the non-terminals as S, and the terminals I am taking the terminals as a P, and the production rules or 2 production rules I'm having, and S is a start symbol. Okay, so now I want to derive an input string. So this input string I need to be derived. Now we can start with the start symbol. So according to the rule we have to start with the start symbol. So start with the S. Now replace S with the production rule. So in place of S I'm going to write AS according to the rule 1. Okay, S is replaced with AS. Now again I'm replacing S with AS because I want to read this string. I want to derive this string. Again replace S with AS. That is S is replaced with AS until you get this string. Check while you're writing A. I'm replacing S with AS because I want to read this string. I want to derive this string. Again replaced S with AS. That is S is replaced with AS until you get this string. Check while you're writing A. Again replace S with AS. So I got 4 A's. I want to get the 6 A's here. Again replace S with AS production. That is S is replaced. So okay. So here there is anything. So S is replaced with epsilon, and you will derive the input string. Whatever the input string want to derive that, I derive by using this protection rule. Okay, so here here the regular expression is A star. It can be generated. Hi students, welcome back. Now let's see another example in the context-free grammar. Let me construct a context-free grammar for the language given. So here they are given a language. For this language, I need to construct a context-free grammar. Okay, the context-free grammar, it means it's consisting of a set of tuples. V, it's a set of non-terminals. T is a set of terminals, and P is a protection rule, and S is a start symbol. Okay, that we know that. So here, by seeing this language, don't confuse. What they are saying that the string can generate for a given language L. Okay, so this is a L, the language. This W, whatever the W that is there, that W belongs to AB. AB multiples, AB star. They are given AB multiples are there. Means W, that is a string belongs to A, B, A, B, B, and AB, AB, BA, BA. So like that, it's a multiples. And C is the constant. Then what is this W and WR? Okay, W is a string, WR is a reverse string. I already explained in the closure properties. W reverse string can be represented as a WR. Suppose if you get AB, W as AB, then WR can be written as a BA. It's just reverse. Okay, suppose if the W is ABB and the WR represented as BBA, the reverse of the W. So here the string, a constant C, and the WR reverse the string. The language is represented like this. So let me write the language strings that can be generated for the given language. Let me write the strings that you can generate for the given language. So in place of A, suppose I have written AA because it is AB's star. So I can write any number of A's, including epsilon. So I can write any number of A's. AA, C is the constant, and the reverse of A is simply AA. And if I write B, A as a B, C is the constant. Reverse of B is B itself. Let me take AB. This time W I have taken as AB. C is the constant. What is the reverse of AB? BA. Okay. So suppose if I take ABB as W, C is the constant. Reverse of W is BBA. So in this way, the strings can be generated for the given language. Okay, the strings that can be generated for the given language. So now let me write the grammar, the protection rule. I need to construct the context-free grammar, right? I have taken any of this input. These are the inputs. I have to take any one of the input and I have to derive this input by using the protection rules. That is the context-free grammar. Okay, by taking any one of the input, I need to derive that input. The grammar could be, what is the grammar? The grammar could be like, starts with the S symbol. It can be ASA and S, it can be BSB, and whatever the S, that should be the C, constant C. Okay, so starts with ACA or starts with BCA. Okay, here in the place of S, you can replace with the C. So these are the protection rules. We call it as a rule number 1, 2, and the 3. Now, okay, now if you want to derive a string, let me take a string. That is the input. Let me take the string as ABBCBBA. I want to derive this string. I want to derive this input string. Now starts with the start symbol. Okay, so start with the start symbol. S determines ASA. Start with the start symbol SASA. Okay, so now I'm substituting in place of yes, I'm writing. Next, what terminal you want? You want terminal B. So write the protection 2. In place of S, I'm writing BSB, and as is A. So in place of A, I have written BSB. Okay, that is from rule 2. Now, so AB is already a terminal. Now coming to the S. Okay, now I want the string. Next is also B. So next I want to B means again I have to replace S with BSB. So S should be replaced with BSB. Write BA as it is according to from rule 2. Okay, so now ABB I got. Next is C. I want to get a C. Okay, S determines C. So in place of S I can write C. Yes, I can write C. BBA is common. ABBCBA according to from rule 3. Did you get the input? Did you derive the input? Yes. ABBCBBA. I derived the Hi students, welcome back. Let's continue with the examples of the context-free grammar. Let me explain you the another example. So construct a context-free grammar for the language L is equal to a power n, b power 2n. Where n is greater than or equal to 1 means the n can be starts with 1 or it should be greater than 1. It should not be 0 or negative. Remember that. Symbol S. So A, S, B, D. Because here the string is starts, you can generate the string. So now the grammar could be, what will be the grammar? The grammar could be, so starts with the symbol S. So A, S, B, D. Because here the string is starts, the starting, you just focus on the first string. First string that is generated by the language. So based on that you need to be right. Okay. So S is determines the A, S, B, B. Okay. Or simply S is equal to A, B, B. Simply write the starting string S is ABB or S determines ASBB. So in place of S, you need to substitute this. Okay. So if I substitute in place of SABB, you'll get AA, BB, BB, BB. You're getting the second string, right? So in that way, you need to be define the grammar. Now, if you want to derive a string, let me derive a string AA, BB, BB, BB. So I want to derive this string. So how can I derive the string? Let me show you. So starts with the start symbol. S determines ASBB. Okay. So next, I want the next terminal should be again A. context-free grammar for the given language. First, take the language and generate what are the strings that we can get. Okay, based on the starting string, you can starting in the second and the third by taking all this thing in your mind and create a grammar for the production rules. By using this production rules, you have to derive any one of this string. Starts with the start symbol. Thank you. Hi students, welcome back. Coming to the next topic in the subject theory of computations is derivations. So far you have seen about the context-free grammar and the different examples of the context-free grammar. Now in this video I want to explain you what is a derivation. Actually, derivation is a sequence of production rules. Okay, so it's a sequence of production rules and which is used to get an input string. Means whatever the production rules you have taken, so how the production rules can be sequenced and which production rule we need to be take, and this derivation is helpful to get the input string. So whatever the input string I'm passing, okay, so that input string I need to get, okay, by using context free grammar. So here the derivation, the concept that we are using, which is a sequence of production rules. So first, which production rule I have to get this input. Next, which production I need to be get. Okay, suppose if to get A, I want to substitute like A, capital A. Okay, the production rule. And next, which production rule I have to be used to get the input string like this. So next time I'll in place of if I want to get a B, in place of A, I substitute BA like this. So whatever the production rule that it is there, but I want the string like this. So for that, the derivation will be useful. A derivation is a sequence of production rules which is used to get the input string. So during passing, we have to take two decisions. So what are the two decisions that we need to be take for the passing? Okay, so first we have to decide the non-terminals which is to be replaced. Which non-terminal has to be replaced? That we have to be considered one point. Non-terminals means you know that the capital letters, capital symbols or non-terminals. So that you know that. So which non-terminal has to be replaced first? And next, we have to decide the production rule by which non-terminal will be replaced. So these are the two decisions that we need to be take. So we have two options to decide which non-terminal can be to be placed with production rule by using two decisions. What are this? You can go for use the leftmost derivation or you can use the rightmost derivation. Okay, the derivation, if you want to derive as a sequence of production rules to use it is which is used to get the input string, we have two options to decide which non-terminal to be placed. Suppose in the production A, capital A, B, small b. So this is a production. Okay, let me take first which non-terminal I have to be replaced. Either I have to replace A or I have to replace B, because these two are the non-terminals. Which production rule, which non-terminal I have to be replaced. So leftmost derivation means I replaced leftmost derivation means I have to replace capital A. Rightmost derivation means first I have to replace, okay, rightmost derivation. So if you are using the rightmost derivation means you have to scan from right to left. So B has to be replaced first. If you are using leftmost derivation means A has to be replaced first. Okay, so see, let's see what is the leftmost derivation and rightmost derivation. After that, see the examples, then you can clearly understand which type of protection rule we have to be applied, whether the leftmost derivation rule or the rightmost derivation rule. First, leftmost derivation rule. Which type of protection rule we have to be applied, whether the leftmost derivation rule or the rightmost derivation rule. First, leftmost derivation rule. In the leftmost derivation, the input is scanned and replaced with the protection rule from left to right. So this you have to be remember. Leftmost means left to right. Left to right you have to be moved. So first take the left hand side non-terminal. First replace that. Then go for the next right hand side. So in the leftmost derivation, the input is scanned. First you have to scan from left to right. So first to see which non-terminal is get first in the left hand side. And with the protection rule, you have to replace that non-terminal. So we have to read the input string from left to right. So let me take this as a protection rule. E is equal to E plus E, E is equal to E minus E, and E is equal to A or B. So these are the protection rule. I want to pass this string A minus B plus A. I want to read this string from left to right, and I want to derive this string. Now let's see. So starts with the start symbol. Let me take E is equal to E plus E. Now the leftmost, what is the leftmost non-terminal? This is the leftmost non-terminal. Okay, here two E's are there. These two are the non-terminals, and plus is the terminal. And first I want to replace E. So in place of E, I can write E minus E because I want this string. You want to derive this input string. So by seeing this input, you have to be replaced. So first I replaced leftmost E minus E. So in these three non-terminals, which non-terminal I have to replace? The leftmost. The left one you have to be replaced. So it has to replace with the A. In place of E, I placed A. So this is over. So non-terminal is you get the terminal, and coming to the next non-terminal, which is on leftmost. Okay, rather than going for the right, first replace with the left. So in place of E, I want to place B because this input string I need to get. So E can be replaced with B. Yes, A minus B plus C. And the remaining non-terminal is E. So replace E with A because I want to pass this input string A minus B plus A. So did you get this string? So this is the leftmost derivation. In the leftmost derivation, the input is scanned and replaced with the protection rule from left to right. So you have to read the input string from left to right. Always remember that. First read equal to E minus A aggregate. So which non-terminal I have to be replaced first? The rightmost you have to be replaced because it is rightmost derivation. I'm scanning the input from right to left. So in this way you have to go. This is the right hand side and this is the Hi students, welcome back. Now let's take the examples on derivation. There is leftmost derivation and the rightmost derivation. So here they are given the question like derive the string. So I want to derive the string ABB for the leftmost derivation. Okay, for the left. Hi students, welcome back. Let's continue with these derivation problems in the theory of computation. Hi students, welcome back. Now let's take the examples on derivation. There is leftmost derivation and the rightmost derivation. So here they are given the question like Hi students, welcome back. Let's continue with these derivation problems in the theory of computation. So here they are given the question like derive a string that is a again in place of A I'm substituting 0 A. Okay, 2 zeros I got. So next one is I need to get 1. Okay, so what's the leftmost non-terminal here? A is a non-terminal, leftmost non-terminal. These two are the. So in place of Vs, I substitute A1B, the first projection. So next, which terminal I need to be take? Non-terminal. The B I have to take because this is the rightmost derivation. From right to left, you need to be scanned. Hi students, welcome back. Let's continue with our problems that we are deriving the leftmost derivations and rightmost derivation. Means we have to derive a string, whatever the string they are given, that string has to be derived by using the leftmost derivation as well as the rightmost derivation. So using the context-free grammar. So this is a context-free grammar they are given. Okay, shall we start the problem? So let's take the solution. First, I want to go with the leftmost derivation. Leftmost derivation. Okay, so in the leftmost derivation, first let me take the pen. So first starts with the start symbol S. So this is a string. Let me write the string here again. A B B A B B A. So I want to derive the string. Okay. So first S should be, you have to take either A B or B A. So here the string will starts with the small terminal A. So I have to replace S as A B. Okay. S is replaced with A B. Now it's a leftmost derivation, means you have to start from the left hand side. So left hand side, this is a terminal. So you don't need to change. Now coming to the non-terminal. This non-terminal should be replaced with this projections. So A. So in the place of B, you have to replace the B with small b, bs or ABB. So according to our string, the next letter that comes from here in the string is sequence is A. So for that, you need to take ABB. So if you take B means the string will be represented as AB, but it is not deriving our input string. If you take the BS, it is not deriving our input string. So I need to take ABB. So the capital B letter, that is a non-terminal, is replaced with ABB. Okay, so this is a terminal and A is also a terminal. Now coming to the first B, okay, I have to take, so B is replaced with the S I'm taking. Okay, the B is replaced with the B. Okay, then the string ABB, B with ABB. Hi students, welcome back. Now coming to the next topic, that is a derivation tree. In the previous video, I explained about what is a derivation. Okay, what are the techniques that we have to follow to derive a string? That is leftmost derivation and the rightmost derivation. Now I want to explain about the derivation tree. Okay, so this one derivation tree. A derivation tree, it is graphical representation for the derivation of the given production rules for a parts tree. The another name for means some properties it has. Almost all computer related subjects we are learning this parts tree. Okay, so the parts tree follows the precedence of operators. The operators are nothing but the place, minus, divide, or all the operators. The deepest subtree traversal first. It is the deepest subtree traversal first. So the start symbol, either it is a E or a S, whatever it may be, the root node should be a start symbol. That is, okay, start symbol. The derivation is read from left to right. So we have to read the derivation from left to right. Okay, suppose whatever the tree that is you are representing, you have to start the reading from left to right. So derivation is always read from the left, starts with this node, left side node, and then go and then node like this. Okay, they're always non-terminal. So whatever the interior nodes that are present, that are the non-terminals. So let me explain you one simple example about the derivation tree. So here I have taken some production rules. This is the production rule. Okay, so E is equal to E plus E, E is equal to E into E, E is equal to A. E can be substituted with A, or it can be substituted with B, or it can substitute with C. And the input string that I need to be passed is A star B plus C. Okay, so what are the steps that we need? If you want, you can go for the step by step, or you can directly implement. Okay, if you want, you can directly go for the step 5 directly. Okay, so starts with E. The E can be substituted with E, derives the E plus E. So E plus E. And step 2, further derivation of the given production. Okay, the operators are nothing but a place, minus, divide. The root node should be a start symbol, either it is a E or a S, whatever it may be. The root node should be a start symbol. symbol. That is, I have taken some production rules. This is a production rule. Okay, so E is equal to E plus E is equal to E into E is equal to E can be substituted with A, or it can be substituted with B, or it can be substituted with C. And the input string that I need to be passed is A star B plus C. Okay, so what are the steps that we need? If you rule and the input string Hi students, welcome back. Let's continue with the examples of the derivation tree. So in the previous video, I explained about what exactly the derivation A productions. So which production I need to take? Hi students, ID star ID plus ID. So construct the derivation tree for this. So how? So starts with E plus E. Okay, and here this is, by seeing this derivation, the first non-terminal is replaced with E star E. E star E. Again, this E is replaced with ID and this E is replaced with ID. What I have to do? So I have to construct the tuples V, T, P, S. Okay, so V is a set of non-terminals is a E here, and the T is a terminals. What are the terminals here? ID is a terminal, plus is a terminal, into is a terminal, brackets are the terminals. So these are all the terminals. V, T, P. P means these are all the production rules. Okay, and S means start symbol. The start symbol here is nothing but E is the start symbol. Okay, shall we continue the problem? Let's see. So let me take first this expression, next this expression. The first expression, derivation tree. So before E plus, so this E first I want to string, yes. Okay, so the thing, this E can be replaced with star E. This production I'm taking, okay, E star E. This E can, this within the brackets, whatever the E production is, that I'm replacing with the first rule, E plus E. So E plus E star E. So next replace with this, E can be replaced with ID plus ID star ID. Did you get this? Did you derive this string? Yes. Okay, so the thing is, what production I need to be take the next, that you have to be find out. If you know that concept, then you can easily draw this derivation. Close the parenthesis. Next. Hi students, welcome back. So far we have seen about the derivations and the derivation tree. That is, the derivation tree means the path tree. If any string is there, how you are going to derive that string by using the leftmost derivation, rightmost derivation, and that derivation, after derivation, you are going to construct a derivation tree. That is a path tree. Now let's see what is this ambiguity in grammar. Which grammar you can say that grammar is having ambiguous, means it is an ambiguity grammar, or it is not an ambiguity. Ambiguous grammar. How can you see? When there is one or when there are more number of one, the way that you can express means if you take the leftmost derivation can be solved in different by using different methods. Okay, means you get the same output, but the way that you are doing is different. Means the presentation is different. So a grammar is said to be ambiguous if there exists more than one leftmost derivation, more than one rightmost derivation, or even more than one path tree for a given input string. So if the grammar is, suppose it is not ambiguous, then you can say it is an unambiguous grammar. Means whatever the input string that you are given, it can generate only one leftmost derivation, only one rightmost derivation, or even only one type of path tree. That type of grammar you can call it as an unambiguous. But a grammar with more than all these things, leftmost, rightmost, and the path tree for a given input string, that grammar is ambiguous grammar. Remember that. If the grammar has an ambiguity, okay, suppose, okay, you thought that what happened? Okay, if it produces more input, more output, means it is okay. In the best, we can take that. We can choose best. But here the grammar has ambiguity, that it is not good for the compiler construction. So for the compiler construction, we need a correct, exact pattern, and we need the single way. But here, if the grammar, whatever we are giving, has ambiguity, then the compiler will, it is difficult to construct the compiler. So it is not good for the compiler construction because it is not able to justify which type of pattern is correct. No method can automatically detect and remove the ambiguity. Okay, so there is no method that can automatically detect and remove the ambiguity, but we can remove ambiguity by rewriting the whole grammar without ambiguity. So that is the that is the only solution that we can remove the ambiguity. Okay, production rules star e within parentheses, and it should be epsilon 0 1 2 up to 9. Okay, so this is a grammar. A grammar consists of VT, PS. We know that it's a context free grammar. V is a set of non-terminals. What are the set of non-terminals here? I and E are set of non-terminals. And what are the terminals? The terminals are plus into brackets epsilon 0 1 2 up to 9. Okay, and P is, these are all the production rules, and S is a start symbol, E is a start symbol. Okay, now we need to check the grammar, whatever they are given, is having ambiguous or not. It is having ambiguity or not. Ambiguity means, is this grammar is producing more than one parse tree or not? Is this grammar is producing giving more than one leftmost derivations, more than one rightmost derivations? Okay, let's check. Let's take any string, but that string should be based on these production rules. For the string 3 star into 2 plus 5, you'll get it out. Ma'am, how can I know only these type of strings I need to take? Okay, so the string that should derive from the production rule, that string you need to be take. Okay, the 3 star 2 plus I is obviously derived from this by using this production rule, either in leftmost or rightmost. How can I say? Because it's a star, E star is the production is there, plus here the terminals. What are the terminals that are there? Star is there, plus is there, and these are all 3 2 5 or all the identifiers are terminals. So that can be derived by using these production rules. So E is a start symbol. In the place of I want to derive this string, so E star E, leftmost derivation. The E can be substituted with I. So I can be substituted with 3, because I can be replaced with 0 1 2 3 up to 9. So I is replaced with the 3. So star, it's already the leftmost derivation. Again E, I'm taking E into A because this is a leftmost derivation. So you have to concentrate only on the left first. Okay, instead of writing I here, I'm again substituting in place of I. Hi students, welcome back. Let's see some more examples to check whether the given grammar is having the ambiguity or not. Okay, we need to check whether this grammar is ambiguous or not. How? So first step is, let's take one string. First AA. So we have to check this string. So here again, this A I'm replacing with, substituting with AA. So in place of A, I'm writing small a because this will be there. So in the second A, so this is a leftmost derivation. So the first non-terminal is over. So next, coming to this is the next non-terminal. After that, this is the next non-terminal. So first come here. This is a non-terminal. So we have to check this string. So here again, A here is generating generation. So please, let's take one string. For the given string, for the string A within parenthesis I'm taking this string. Okay, because this string can be derived by using this production. So the above grammar can generate 2 parse tree. It can generate parse tree, then string A terminal is over. First brackets. So next the symbol is A. So but parse trees. Since there are 2, it is this string is I. So in C rule. Okay, so next A, and this time I'm taking this A within parenthesis. A with string this production, because A determines the second, and string is proving that the given grammar is ambiguous or not. So starts with this A. So again A. So this A is replaced with the A, and this is small a. Again this A is replaced with the A, and this will be replaced with this production, because A determines the second rule. Okay, and this will be replaced with the, and this is A. So did you get this string? A within parenthesis A within parenthesis A, and A. So this string I can represent it in another way also. See here, A in a parse tree. Hi students, welcome back. Let me take another example to explain whether the given grammar is ambiguous or not. So from the above grammar, I'm just taking the string like id plus id minus id. So this is a string. So this string can be derived in 2 ways. Okay. So first let me take one way. That is I'm using the leftmost derivation. So the E starting string is the starting symbol is E. So E can be substituted with E plus E. So that this is a leftmost derivation. So in place of E, I can write id. So here is E is leftmost non-terminal. This is I represented in 2 ways: ambiguous or no. A B B. The above grammar can generate 2 parse trees. So how? Let's see. Starts with the start symbol S. The S I'm replacing with SS. Given grammar can be deriving 2 parse trees. First E plus E. Next E is replaced with ID. Next this E is replaced with E minus. I can represent given is ambiguous or not. So how? Let's see. Starts with the start symbol S. The S I'm replacing with SS. I'm replacing with SS. So this S I can replace with epsilon. Epsilon B I need to get. So again I'm dividing this. I'm substituting this S with ASB. A, ES, B. Okay, so these are all terminals. The only non-terminal that is remaining here is the S. So this S I'm replacing with epsilon. So what the string that you get? Forget about the epsilon because epsilon is empty. A, B, B. You got the string? Yes. So let me take the another type of representation here. Start with the start symbol. So instead of this projection, I'm taking ASB. ASB. So the first A, second, last B for the given input. So here I'm ABB. So the string I read the string. So this S is replaced with epsilon, empty string. So this is another way of representing the path string for the given input. Hi students, welcome back. Coming to the next topic, that is a simplification of context-free grammar. Okay, so you have seen so many examples on the context-free grammar, and in the context-free grammar, you're worked on the ambiguous grammars and unambiguous grammar also. Now, all the grammars, whatever you're taking, are not always optimized. That you have to know. Okay, so all grammars, whatever the context-free grammars or whatever the grammars that you're taken, that are not always optimized. That means the grammar may consist of some extra symbols. Okay, so there is a option means the grammar, whatever the production rules that you're taken, that production rules may consist of some extra symbols like non-terminals, which are increase the length of the grammar. So we have to reduce the grammar by removing useless symbols. So how can you simplify the context-free grammar? How can you simplify the context-free grammar? By removing some useless symbol. Useless symbols. The useless symbols may be the epsilons, or the useless symbols may be the non-terminals. So that are not used in the program. If they're not used in the deriving the string, then we can say that symbols are the useless symbols. So if you remove that symbols, then we can reduce the length of the grammar. Okay, by providing these extra symbols, it increasing the length of the grammar, whatever the grammar that we are using. So the properties to reduce the grammar, or let me write the properties. The properties to reduce the grammar. What are the properties that we have to be followed? Let me tell you the properties. So the properties to reduce the grammar are, first, each non-terminal and terminal of G, each non-terminal and terminal of grammar, whatever the grammar that you're taking, that's the context-free grammar that you're taken. In the grammar, each non-terminal and terminal appears in the derivation of some word in language, So remember that. And the second property, there should not be any projection as like x determines y. So these two are the non-terminals. There should not be any projection like this in manner, where x and y are non-terminals. So there should not be like this. Terminals. And the third property, if epsilon is not in language, let us take if epsilon, the empty string is not in language, and then there need not be the projection. Like x determines epsilon, not only the x or y, whatever it is. So that non-terminal is determines the epsilon. Okay, so these are the three properties that we have to that are reducing the grammar. So in simple words, I can simply say that reduce grammar. What is reduce grammar? The reduced grammar is nothing but it's a removal of useless symbols. The useless symbols are the symbols that are not used in deriving the epsilon production, and removal of unit production. Okay, so this is in this way we can simplify the context-free grammar. The simplification of context-free grammar is nothing but the reducing the grammar size. Okay, so that the performance can be increased. To reduce the grammar, we can remove we can use the removal of useless symbols, elimination of epsilon production, and removal of unit production. How we can remove the useless symbols in the production? How we can eliminate the epsilon productions in the grammar? And how we can remove of a unit production in the grammar? So this all we will see in the next videos one by one. Thank you. Hi students, welcome back. Let's continue with these reduced grammar, that is the simplification of context-free grammar. I said the simplification of context-free grammar can be done by three methods, that is removal of useless symbols and elimination of epsilon productions and the removal of unit productions. So let's see the first one, the removal of useless symbols. How you can remove the useless symbols? First of all, how you identify the useless symbols? Now let's see. A symbol can be useless if it does not appear on the right-hand side of the production. Okay, the symbol that is useless, when you consider the symbol is useless, if it does not appear on the right-hand side of the production and it does not take part in the derivation of any string, that symbol is a useless. Okay, a symbol that is does not appear on right-hand side it is not everything. Okay, at the same time it does not take part in the derivation of any string, whatever the string that we are taken, if it is not helpful in deriving any type of the strings, that production you can eliminate, because if it is not doing any operation on the strings, then we can say it is no useless, only the wastage of memory. That is the removal of useless symbols. Here I have taken one type of production. So in this context-free grammar, how can I identify the useless symbols? So here T determines, this is a start symbol. The start symbol has to, first of all, the start symbol has to take all the non-terminals. So here it is A is taking, B is taking, and the T itself is also considered, but C is not considered. Did you observe? In the start symbol, there is no C. Okay. If in the start symbol it is not there, the right hand side projection is not having the C non-terminal, either in the remaining projections is it present? No. In the remaining projections also, right hand side it is not present. The C, the non-terminal is not present on the right hand side. That they are saying. A symbol can be useless if it does not appear on the right hand side. So this C is not appear on the right hand side of the projections. Are you observing? This C is not present on the right hand side. This is left hand side and this is right hand side. Take your hands. Okay. A symbol C that is not appearing on the right hand side of the projection and it does not take part in derivation of any string. Here we are not use the C. Okay. D is not, we didn't use the D terminal. So that string I can say useless. So here the variable C is useless because it is never occurring in the derivation string. So we can eliminate the C. Now coming to, is there still any projection rule sorted that is useless? See here. A determines AA. So what is our rule? What the string that has to be passed in the way that the projection, the right hand side should be the terminals, non-terminals, and the left hand side should be the terminals. It should contain, the left hand side should be non-terminals. Left hand side should be non-terminals and right hand side should be replaced, all the non-terminals as replaced with the terminals. Then it can pass the input string. So if you take A determines AA, if you substitute here, let me take, here this is also useless. How can I say this is useless? A determines A is also useless because there is no way to terminate. It can never produce a string. What it means? Let me take the projections again. Should be, and the left hand side should be the terminals. It should contain, the left hand side should be non-terminals. Left hand side should be non-terminals and the right hand side should be replaced, all the non-terminals as replaced with the terminals. Then it can pass the input string. So if you take A determines AA, if you substitute here, let me take, here this is also useless. How can I say this is useless? A determines A is also useless because there is no way to terminate. It can never produce a string. What it means? Let me take the projections again. So T determines AAB and ABA and AAT. Now A determines AA. That's it. Okay, and B determines AB and B. So C is anyhow I discard it because it is not accepting any the right hand side, this non-terminal is not used in the right hand side. Now I'm saying this is also useless. How can I say this is useless? Suppose if T determines AAB, if I substitute in place of B, AB, if I substitute in place of AB, okay, or if I substitute in place of B is B, it's generating complete terminals. Okay, it has to derive. We have to replace all the non-terminals with the terminals in the right hand side. That is our grammar itself. Okay, our concept is the non-terminals in the right hand side should be replaced with terminals. So until it gets all terminals. The first is okay. Now let me take the second projection. T determines ABA. Suppose in place of A, if I substitute AA, okay, still it is a non-terminal. Okay, if I do like this only, in place of A, again I substitute AA, still a non-terminal is present. So how long you are doing the same thing, still a non-terminal is presenting, but which is a violation because all the non-terminals in the right hand side should be replaced with the terminal. So until it reaches the terminal, then you can say that is a right projection. If it is not reaching to the terminals, all terminals, it is not a right projection. Okay, so to remove this useless projection A determines AA, we will first find all the variables which will never lead to terminals. So here we will not leading to the terminals string such that as a variable A. So then we will remove all the projections which vary B occurs. So we can remove this projection completely. So the simply after elimination, after removal of useless symbols, what are the new projections that we get? Hi students, welcome back. Now coming to the next continuation of this simplification of context-free grammar. In the previous video, to reduce the given grammar, we have to do three things. One is the removal of useless symbols and elimination of epsilon projections or elimination of unit projections. This we have to do. Now coming to the second one, the first one I explained. Now let's see the second one, removal of elimination of epsilon projections. So if the epsilon projections, that is the empty projections, the projection S determines epsilon are called the epsilon projections. Not only the start symbol or whatever the non-terminals that are that, if that determines the epsilon projections, that we have to be removed. These types of projections can only be removed from those grammar that do not generate epsilon. So for this also you have to follow some rules to eliminate the epsilon projections. First, find out all nullable non-terminals which derives epsilon. Means whatever the non-terminals that are there, the start symbol or whatever the non-terminals that are present, first we have to find out whether these non-terminals are deriving epsilon or not. Is deriving epsilon or projections or not. Second step, suppose if it is deriving epsilon projection. For each projection, A determines A, means some projection you are getting on right hand side. Construct all projections A determines X, where X is obtained from A. So this new projection is obtained from A by removing one or more non-terminals from step 1. So don't be confused. you see the example, then you can easily understand these properties, these steps. So for now, combining the result of step 2 with the original predictions and remove the epsilon predictions. So let's see the example. So see example clear. Removing one or more non-terminals from step 1. So don't be confused. If you see the example, then you can easily understand these properties, these steps. So for now, combining the result of step 2 with the original predictions and remove the epsilon predictions. So let's see the example. So see example carefully. So here you can see S determines x by x. Okay, this is one prediction. In this prediction, x is determining 0x and epsilon. Means x can be replaced with epsilon. And here also y determines 1y, or also y determines the epsilon. So I want to remove these two predictions, because I'm eliminating the epsilon. So you can't simply remove these predictions. If you simply remove this prediction, you can't reach to the string. Okay, you can't reach to the, our condition is whatever the non-terminals that are present on the right hand side should replace with the terminals, and finally it has to reach the terminal symbol. Suppose you simply replace epsilon, okay, by just removing without doing any operations. If you remove, in place of x, if you substitute 0x, in place of y, if you substitute 1y, okay, you'll get the string like this. Means whatever the operations you are doing, you're getting x by x or repeating like that. You're not, then you can say this prediction is, it's wrong. Okay, means this is not the context free grammar. You can clearly say that. So don't do like that. So you have to follow the rules, and you have to eliminate the epsilon predictions without disturbing the given context free grammar. So how can I do? Let's see. While removing epsilon predictions, we are deleting the rule x determines epsilon and y determines epsilon. To preserve the meaning of context free grammar, this point you have to remember that. To preserve the meaning of the context free grammar, we are actually placing epsilon at right hand side wherever x and y appear. So just place epsilon on right hand side wherever x and y are appear. Then you'll get some predictions, and in place of epsilon you can write the predictions. So let me take the first prediction. S determines x y x. First, if first x at right hand side is epsilon, then you'll get, suppose if this x is an epsilon, you will get s determined by x. Similarly, if the last x, if you take this last x is an epsilon, then you'll get s determined xy. Suppose y is an epsilon, you'll get xx. Suppose if both y and x, these two are epsilon, you'll get only s determines x. This time, if both x are epsilons, then you'll get simply y. So I'm placing epsilon, and I get some different predictions on the right hand side. So finally, s I can replace with xy, yx, xx, xy. Okay, so this prediction I have written like this. I have changed it like this. Now I can freely remove the x determine x and y determine y in the case of this s prediction, because after substituting only I got these predictions. In the same way, now consider the remaining predictions. X determines 0x or epsilon. Okay, so if we replace epsilon at the right hand side for x, if you replace epsilon at the right hand side of the x, you'll get x determines 0. Okay, now the new prediction is x determines 0x or 0. In similarly, y determines 1y or 1. So finally, the context free grammar with removal of epsilon predictions is this grammar. I remove the epsilons and rewrite the predictions rules like this. Now these predictions rules are equivalent to the prediction rules whatever that with epsilon. So with epsilon, and this is without epsilon prediction rules. Thank you. Hi students, welcome back. Now let's see the third one. Hi students, welcome back. Now coming to the next. Get xx on terminals which derives epsilon. Means whatever the non-terminals that are the star symbol, or whatever the non-terminals that are present, first we have to find out whether these non-terminals are deriving epsilon or not. Is deriving epsilon or predictions or not. Second step, suppose if it is deriving epsilon prediction. For each prediction, A determines A, means some prediction you are getting on right hand side. Construct all predictions A determines X, where X is obtained from A. So this new prediction is obtained from A by removing one or more non-terminals from step 1. Hi students, welcome back. Let's continue with the non-terminals, and the left hand side should be the terminals. Also, right hand side eliminate, because if it is not doing any operation on the strings, then we can say it is no useless, only the wastage of memory. Non-terminal of any string. Here we are not, right hand side should be and B. So C is anyhow I discard non-terminal table A. So then we will read this prediction also. B determines A B A. So this is our new. Hi students, welcome back. Now coming to the next continuation of this simplification of context free grammar. In the previous video, to reduce the given grammar, we have to do three things. One is the removal of useless symbols and elimination of epsilon or whatever the non-terminals that are. So for now, combining the result of step 2 with the original predictions and remove the epsilon. because I'm eliminating the epsilon. So you can't simply remove these productions. If you simply remove this production, you can't reach to the string. Okay, you can't reach to the, our condition is whatever the non-terminals that are present on the right hand side should replace with the terminals, and finally it has to reach the terminal symbol. Suppose you simply replace epsilon, okay, by just removing without doing any operations. If you remove, in place of x, if you substitute 0x, in place of 5 you substitute 1y, okay, you'll get the string like this. Means whatever the operations you are doing, you're getting x, y, x, x, y, x, or repeating like that. You're not, then you can say this production is, that's a wrong, okay, means this is not a context free grammar. You can clearly say that. So don't do like that. So you have to follow the rules and you have to eliminate the epsilon productions without disturbing the given context free grammar. So how can I do? Let's see. While removing epsilon productions, we are deleting the rule x determines epsilon and y determines epsilon. To preserve the meaning of context free grammar, this point you have to remember that. To preserve the meaning of the context free grammar, we are actually placing epsilon at right hand side wherever x and y appear. So just place epsilon on right hand side wherever x and y are appear. Then you'll get some productions, and in place of epsilon you can write the productions. So let me take the first production. X determines x, y, x. First, if first x at right hand side is epsilon, then you'll get, suppose if this x is an epsilon, you will get s determined by x. Similarly, if the last x, if you take this last x is an epsilon, then you'll get s determined xy. Suppose y is an epsilon, you'll get xx. Suppose if both y and x, these two are epsilon, you'll get only s determines x. This time, if both x are epsilons, then you'll get simply at right hand side is epsilon. Suppose if y is an epsilon, you'll get xx. Suppose if both y and x, these two are epsilon, you'll get only s determines x. This time, if both x are epsilons, then you'll get simply y. So I s determines x. This time, if both x are epsilons, then you'll get simply y. So I'm placing epsilon and I get some different productions on the right hand side. So finally, s I can replace with xy, yx, xx, xy. Okay. So this production I have written like this. I have changed it like this. Now I can freely remove the x determine x and y determine y in the case of this s production, because after substituting only I got these productions. And the same way I got this in the case of this s, this grammar. I remove the epsilons and rewrite the productions rules like this. Now these productions rule are equivalent to the production rules whatever that with epsilon. So with epsilon at right hand side of the x, you'll get x determines 0. Okay. Now the new production is x determines 0x. 2 or epsilon, you'll get only s determines x. This time, if both x are epsilons, then you'll get simply y. So I different productions on the place with x, y, y, x. This production I have written like this. I have changed it like this. Now I can freely remove the x determine x and y determine y in the case of this s production, because after substituting only I got these productions. And the same way, now consider the remaining productions x determines 0x or epsilon. Okay. So if we replace epsilon at the right hand side for x, if you replace epsilon at the right hand side of the x, you'll get x determines 0. Okay. Now the new production is x determines 0x or 0. In similarly, y determines 1y or 1. So finally, the context free grammar with removal of epsilon productions is this grammar. I remove the epsilons and rewrite the productions rules like this. Now these productions rules are equivalent to the production rules whatever that with epsilon. So with epsilon, and this is without epsilon production rules. Thank you. Hi students, welcome back. Now let's see the third one, that is which are used for simplification of context free grammar, means to remove the to reduce the grammar. The third one is removing the unit production. So far you have seen that the eliminations of the epsilon productions and eliminating the useless productions. Now let's see the removing of unit production. So what productions you call it as a unit production? What type of productions you call it as unit production? The unit productions are the productions in which one non-terminal gives another non-terminal. Means one non-terminal is giving another non-terminal. One non-terminal is giving another non-terminal. These type of productions you call it as a unit productions. So we have to remove these type of unit productions so that we can reduce the grammar size. How you can remove that? So for that you need to follow the steps. To remove x determines y, add a production. So this production has to be add, where you have to add this production. So add a production x determines a to the grammar rule whenever y determines a is occurs in the grammar. So after adding, you can simply delete the x determines y. So without adding, you can't remove the x determines y. And repeat the step 1 and step 2 until all unit productions are removed in the given grammar. Let me show you the example, then you understand. We can reduce the grammar size. how you can remove that. So for that, you need to follow the steps. To remove x determines y, add a production. So this production has to be added, where you have to add this production. So add a production x determines a to the grammar rule whenever y determines a is occurs. In the a determines 0s and a determines 0 0 and b determines in the given grammar. Let me show you the example, then you understand. So here I have taken a production rules. S determines 0a, 1b and c, and a determines 0s 0 0 and b determines 1a and c determines 0 1. So I'm just rewriting here. S determines 1b and s determines c. A determines 0s and a determines 0 0 and b determines 1 and b determines a and c determines 0 1. So in this, what are the unit predictions? Simply you can say these are the unit predictions. These two are the unit predictions because one non-terminal, it determines the another non-terminal. I want to remove these two non-terminals, two unit predictions. How I can remove that? So first you take S determines C, which is a unit prediction. But while removing the S determines C, we have to consider what is a C. That C gives, that you have to add in this prediction. Means instead of ASC, you have to replace with 0 1. S determines 0 1. So in place of C, just replace with 0 1 so that the unit prediction can be removed. There is no use of using this now because S determines 0 1 is same as C determines S. In the same way here also, the big A can be replaced with either 0S or 0 0. So just remove this prediction and write B determines 0s or 0 0 because A is determining two predictions, 0s as well as 0 0. So finally I can write these predictions as S determines 0A, 1B. In place of C I'm writing 0 1. A determines 0s and 0 0. B determines 1. In place of A I'm writing 0s and 0 0. And C is determines 0 1. So here I eliminate the unit prediction. So there is no concept of unit predictions here because all every non-terminal is determines the a terminal with non-terminal. That's it. So this is how you can reduce the Hi students, welcome back. Coming to the next topic, that is a Chomsky normal form, CNF. So far you have seen about the CFG, that is a context-free grammar. CFG means context-free grammar, whereas CNF is Chomsky normal form. So don't be confused, it is FG. Whenever you are seeing this context-free grammar, CNF is Chomsky normal form. So what is this Chomsky normal form? CNF stands for Chomsky normal form. A context-free grammar is in CNF if all production rules satisfies one of the following conditions. When you can say that the given grammar, that is a context-free grammar, is in CNF. If all the production rules are following any one of these conditions, then we can say that the given grammar is in Chomsky normal form. Okay, so the production rules, whatever the production rules you are seeing with the starting symbol and with non-terminals on the left hand side and the terminals and the non-terminals that are present on the right hand side, that productions you call it as a context-free grammar. That we know that. So all the production rules are in the form of context-free grammar. If you want to find out whether the given context-free grammar is in the Chomsky normal form or not, these conditions are simply generating the. See a simple example whether we have to which grammar is in Chomsky normal form and which is not in Chomsky normal form. See here. Here S determines AB. Okay, this is one context-free grammar. I taking two context-free grammars. In these two context-free grammars, I need to find out whether this grammar is in Chomsky normal form or not. Here S determines AB. Is it following Chomsky normal form? Yes, because non-terminal has generating two non-terminals. One single non-terminal is generating two non-terminals. That is the second rule. Okay, it is following that. S determines C. Okay, S determines C, which is generating a terminal. So it is in Chomsky normal form. And A determines A. Okay, A determines A. This is also Chomsky normal form, but according to the third rule. Okay, according to the third rule. A non-terminal is generating a terminal. That is a third rule. See here. A non-terminal generating a terminal, then you can say that the production is in Chomsky normal form. So either it has to generate an epsilon, or it has to generate two non-terminals, or it has to generate a single terminal. So here it is following each production is following any one of the Chomsky normal form production rules. Okay, then you can say G1 satisfies the rule specified for Chomsky normal form, so it is in CNF. So the given grammar G1 is in Chomsky normal form. The given context-free grammar is in CNF by applying the rules. Now let's see these grammar. S determines A is in Chomsky normal form? No. How can I say? Because according to our rules in the Chomsky normal form, either the grammar has to generate an epsilon, either a single non-terminal is generating two non-terminals, either it can a non-terminal is generating a terminal. So these are the three rules that it has to be followed. Either any one of this rule. But here it is following S determines S is generating a non-terminal as well as a non-terminal. Okay, and A determines A. So okay, this is according to the third rule, this will be the correct. It is in Chomsky normal form, and this production is also in CNF. Only this production is not in CNF because this production is following with the terminal. A terminal is followed with a non-terminal, which violates the Chomsky normal form rule. So you can say G2 does not satisfy the rule specified for the Chomsky normal form, as S determines AA contains a terminal followed by non-terminal, which violates the Chomsky normal form rules. So you can clearly say G2 is not in CNF. I hope you understand what exactly the Chomsky normal form. If a given grammar is in if it is in Chomsky normal form, means it has to follow these rules. So remember these rules, don't forget these rules, because if you know the rules, then you can easily identify whether the given grammar is in CNF or not. Suppose if it is not in CNF, we need to convert into CNF. Okay, so here it is not in CNF. If it is not in CNF, it is a context-free grammar only, but it is not in CNF. So how we are going to convert the given grammar into Chomsky normal form, that I will explain in the next video. So first learn this basic concept. If you understand these rules, then you can easily find out whether the grammar is in CNF or not. If it is not in CNF, then you can find out how to convert the CGF, that is a context-free grammar, into CNF. Thank you. Hi students, now let's see the steps for converting the context-free grammar into CNF, that is a Chomsky normal form. In the previous video, I explained what is a Chomsky normal form. If any grammar is not in CNF, how can you say that it is not in CNF? If it is not following any one of the rules of the Chomsky normal form. What are the rules of the Chomsky normal form? Just recall it. The first rule is either the production contains the start symbol should have contained epsilon, or any non-terminal, okay, any non-terminal is followed with two non-terminals. Okay, any non-terminal is following with two non-terminals, then you can say that the given grammar is in Chomsky normal form. Okay, non-terminal is determines two non-terminals, then it is in CNF. Or a non-terminal is generating a terminal, then it is in CNF. So these are the three rules that it has to follow. Any one of the condition has to be satisfied in the production, either this or this or this. Okay, then you can say that the grammar is in CNF. Suppose if it is not in CNF, that is it is only generating a single symbol, or it is only generating a terminal with a non followed by non-terminal, then you can say that the grammar is not in CNF. Let's see how to convert the steps. The steps for converting the context-free grammar into Chomsky normal form. First, eliminate the start symbol from the RHS. So if you want to start with, first eliminate the start symbol from the RHS. So if the start symbol T is at the right hand side of the production, create a production as. Okay, so you have to start, suppose S is the start symbol, just replace that. Eliminate the start symbol from the right hand side. So you have to eliminate the start symbol from the right hand side like this. So here I'm just taking a new start symbol S1, and that S1 you can replace with a S. So this is the first step to converting the context-free grammar into Chomsky normal form. So create a new production, that is a new start symbol. S1 determines S. S is our previous start symbol. Now I'm replacing the S with S1. Okay, S1 with S. So what? Second step. In the grammar, remove the null, unit, and useless production. So the first thing is in the context-free grammar, try to remove the, that is, we are simplifying the context-free grammar. If you want to convert into Chomsky normal form, first you need to simplify the context-free grammar. How you are going to simplify the context-free grammar? By removing the null productions, by removing the unit productions, and by removing the useless productions. So that I already explained in the previous video. If you want to know how to remove those null, unit, and useless productions, just follow my previous videos. So that, okay, which is a simplification of the context-free grammar. Now let's see. The second step is, here these are the steps for converting CFG into CNF. So first thing is you have to create a new production for the start symbol, and the second thing is remove the null productions, unit productions, and useless productions if that are present in, if anything present in the context-free grammar. Okay, I removed it. Next, eliminate the terminals from the right hand side of the productions if they exist with other non-terminals or terminals. Suppose if the grammar is in like this, which is violating the Chomsky normal form. It is a context-free grammar, and it is also the useful grammar production only, and it is not a null product, and it is not a unit product also. Okay, so I remove all the null productions, unit productions, and the useless productions, but still my grammar contains these type of productions. So if these type of productions are there, try to eliminate terminals from the, what are the terminals here? A is the terminal. Try to eliminate the terminals from the right hand side of the projection if it exists with other non-terminals on the terminals. So suppose if it is, the projection is like this, I want to create, I can be decomposed as, okay, this projection I can be decomposed as. So S determines A is my projection, which is violating the Chomsky normal form. I want to convert it into Chomsky normal form. How? I'm just decomposing it. Decompose it means I'm going to divide this projection as S determines R A and R is replaced with A. So both are the same. So finally you will get S determines A only. In place of R, if you substitute small letter A, you will get this projection only. So but I decompose this step, single projection into two projections so that it is in Chomsky. It is in CNF. How can I say it is in CNF? Because one non-terminal is producing two non-terminals. That is the second rule, and one the terminal non-terminal is generating a terminal, which is the third rule of Chomsky. So now it is in CNF. So if you want to make a projection into CNF, you want to decompose it with two projections. So replaced with a non-terminal, and that non-terminal is determines the terminal. I hope you understand how I'm just changing the context-free grammar into CNF. Next, eliminate RHS with more than two non-terminals. Suppose there are more than two non-terminals. Here S determines ABS. Here three non-terminals is there, but we want only two non-terminals. Then what you're doing? So replace with S determines RS means this AB I'm replacing with R. Okay, S determines RS and R is nothing but AB. R is substituted with AB. Finally, you will get this projection only. If you substitute in place of R, if you substitute AB, you will get S determines ABS only. Okay, but I just decompose this single projection into two projections and I make these projections which are in Chomsky normal form. Okay, if the given grammar is in the right hand side, if it is more than two non-terminals, just decompose it like this. S determines RS, R is nothing but AB. So these are the steps to convert the context-free grammar into Chomsky normal form. So in the next video, I'll explain with an example, then you can get a clear idea what is exactly the Chomsky normal form was. Thank you. Hi students, let's continue with the Chomsky normal form. In the previous video, I explained what is the Chomsky normal form and what are the steps that you need to consider while to convert the context-free grammar into Chomsky normal form. So now apply those steps in this example. So here they are given an example like convert the given grammar, that is a context-free grammar, to Chomsky normal form. So this is the grammar they are given. We have to convert this context-free grammar to CNF. So first of all, see whether this grammar is in CNF or not. They are saying, okay, even though they are saying, let's see, let's observe that grammar, whether it is in CNF or not. What are the rules for CNF? Either the start symbol should generate an epsilon, okay, and any non-terminal will have the, it's generating two non-terminals, only two non-terminals. Single non-terminal is generating two non-terminals, not more than two. And a terminal, non-terminal is generating a terminal. So these are the rules for Chomsky normal form. So let's see, is this projection is following these rules or not? So here the first projection is following the rule and the second is not following the rule. If it is not following the rule means we have to decompose that. And this is also not following. Here the tree is there and it is also not following. A determines epsilon, it is following the rule, and this is also not following the rule, and B determines B is following the rule. Means some projections are not following the Chomsky normal form. We need to get all the projections had to follow any one of the Chomsky normal form rule. Now let's convert it. We will create a new projection. So what is the first step for converting? The first thing is you have to take a new start symbol. You have to replace a new projection. So for that you have to create S1 determines S. So S is equal, S determines AAB, and A determines ABB epsilon, and B determines AAB. So first step is I'm just adding a new projection. That is a new projection. Okay, now coming to the second step. So what is the second step? The second step is as grammar G1 contains A determines epsilon, okay, that is a null projection, we have to remove it. Okay, if any null projections are there, that is in if it is the start symbol has to contain the null projections, but here the grammar itself is contains the null projections, so only the start symbol has to contain null projection according to our rule. But so it contains a null projection. So if any null projections, if any unit projections, or if any useless projections are there, try to remove that to generate the Chomsky normal form according to our rules. Okay, so we have to remove epsilon. We have to remove epsilon. So that is S1 determines, I'm replacing it, S1 determines A, S determines A, B. Now coming to A determines A, B, B, I'm removing the epsilon. So whenever the A is present in that A place, I need to write a new projection. Okay, so A determines A, B, B, I just remove the epsilon, and in the place of B, the B contains A, B. Okay, if I place epsilon here, okay, in the place of A, if I place epsilon, I'll get a single variable A. Here also and here also, if I replace A with epsilon, I'll get a single variable terminal A. So you have to write the terminal also. So this is the way you have to remove the null projection. Whenever the A determines epsilon is there, so replace A with epsilon. Replace A with epsilon and write that projection. Write that terminal. If it is a terminal or non-terminal, whatever it may be, that terminal has to be added to this production. So this is how you have to replace that. So add A in the B production. Okay. Now still check. This G1 contains a unit production is there. So to make a grammar Chomsky normal form, we have to simplify the context-free grammar. I already said you have to simplify the context-free grammar. If you want to simplify context-free grammar, what are the steps you have to follow? Remove null production, remove unit production, and remove useless productions or eliminate useless production. So this I already done. Okay, I removed the null productions. Now I need to check still anything is useless is there. So here the unit production is there. Means S determines S means one terminal is determined, one non-terminal is determining another non-terminal. So which is a unit production. I want to eliminate this unit production. Okay, now let's eliminate the unit production. So here we have to replace S with B. So to eliminate unit production, don't be confused. We are following the step-by-step procedure. First, I'm trying to convert the given grammar into Chomsky normal form by following these rules. If there is anything simplification is needed in the context-free grammar, first try to simplify that and then apply the rules. So to eliminate unit production, so replace. So S determines B. This is also unit production. So here not an S1. S determines B also unit production. So replace B with B production rule. So whatever the B production rules are there, that should be replaced here. Production rule. So now let me write. So in place of yes, I'm replacing with S production. S1 determines. So what is the S here? I'm replacing with S production. So don't confuse. Let's see. I'm just replacing the unit productions. Unit production. So in place of yes, I'm writing the S productions. And S is as usual. Okay. And here, in place of B, S1 determines B. So I have to replace this B also with the B productions because I'm eliminating the unit production. S determines B is a unit production. So in place of B also, I want to replace the B production. So what are the B productions? AA, BA. Okay. So AA, BA. So A is already there. So I'm not writing here. In place of B, I'm writing AA, B. So S is. Now A contains ABB and B contains AA, BA. So now that null productions are over and I eliminated the unit productions also. Is there any useless production? I don't think so. Is no useless productions are there. Okay. Now let's see the third step. Now so the production rule. Whatever we are getting now here is this. Also remove the unit productions and we get a new productions now in the production rule. This is step 3 I'm taking. Step 3 in the production rule, S1, that is the S0 I'm taking, AA, I'm just taking some productions in that which are violating the Chomsky normal form. AA, and A determines ABB, and B determines AA. So these are the some productions which are not in Chomsky normal form. S1 determines A, which is in CNF, and S1 determines B is also in CNF. Only these two are not in CNF. And again, this is also not in CNF. And this is also not in CNF. B determines B is in CNF and B determines A is in CNF. Okay, only these four productions are not in CNF. So that's why I have written like this. Only these are not in CNF. Here the terminal A exists on the right hand side, which is followed with a non-terminal. So we will replace terminal A with X. So let me take a new variable X. So I take in, and I just want to replace with X wherever the A is present. Okay. So now the productions are S0, A. In place of A, I'm writing XA, Chomsky normal form. So this is also in CNF. Hi students, now let's see GNF. So far you have seen about the CNF, that is the Chomsky normal form. What is the Chomsky normal form? What are the steps to convert the context-free grammar to the Chomsky normal form, and the example on conversion. Now coming to the another type of the normal form, that is a Greback normal form. Okay, GNF, that is a Greback normal form. A context-free grammar is in Greback normal form if all the production rules satisfy one of the following conditions. If whatever the production rules that in the context-free grammar, in that context-free grammar, it has to follow any one of these conditions. Let's see what are these conditions. A start symbol generating epsilon. So whatever the start symbol that is there, that it can generate epsilon, then you can say that that a particular production is in GNF, Greback normal form. A non-terminal generating a terminal. Okay, a non-terminal is generating a terminal. And the third one is a non-terminal generating a terminal, which is followed by any number of non-terminals. So this is the only difference between the Chomsky normal form and the Greback normal form. Okay. In the Chomsky normal form, the start symbol is going to generate the start symbol is generating an epsilon, or a non-terminal is generating a terminal, or a non-terminal is generating more than. It's only two non-terminals, not more than. It's only two non-terminals should be there. So this is Chomsky normal form. Whereas Greback Hi students, now let's see what are the steps for converting the context-free grammar into readback normal form and with an example. So before going to example, let me explain you the steps. The first step is convert the grammar into CNF. So whatever the context-free grammar is given, that first you need to convert it into Chomsky normal form. Okay, so Chomsky normal form, what are the steps for converting for CFG to CNF? It has to generate the start symbol, means the new production has to be taken as a start symbol, okay, and replace the start symbol with a new. Please keep concentrated here. So this is a to check whether the grammar is production rule into Chomsky normal form into whatever the given context. Oh, these are all in GNF. Only these two are not in GNF. But it is a left recursion. It is provided A, B, A, A. So this is what means the new production